Hello everybody, as I always say, Andariki Namaskaram, Ellargu Swagatam and a very warm welcome to Vedanta J English channel. This is me, your master teacher Nabamita Ma'am, and today we are going to complete P block and periodic properties in about 3.5 hours. I believe that we will be able to complete both the chapters, and please remember that this year these are the easy kill chapters and you will be able to get maximum marks from these chapters because they are easy. And also from P block, the repetitive part or the so-called tougher part where you were asked about oxidation states of oxo acids of sulfur or chlorine or phosphorus, all of those have been deducted, right? But it may come from the redox reaction part. So hence, I have noted it down in my notes and I will be sending you the notes so you can go through it, but I will not be teaching you right here. You know how to find oxidation state. I have taught you many a times before this, so I'm not going to go through that, okay? All right, everybody. Now I know that I was taking this session live, but then my internet was not supporting me and it just went off. It did not, it's still not running. So I have to record and then I have to run to the office. I have to upload it. So yeah, it's a lot of work, but I'm going to do it because you have your exam, everybody. Before I start with the session, here is a quick look at the schedule of Vedanta J English channel for 8th of January to 12th of January, everybody. I was supposed to take this session Monday, that is yesterday at 9 p.m. However, I thought that it is better to take it in the morning or in the afternoon session when you all will have a fresh mind and you will be able to grasp the concept because like I just told you, it's an easy chapter and I don't want you to spend so much time. So 3.5 hours, 2 chapters you can complete and you can just solve the PYQs later on, right? Now tomorrow, that is Wednesday, you will have mole concept and solutions that I will be taking. Once again, 2 chapters we will be completing. Binomial theorem at 9 p.m. by Nabamita Ma'am, I guess. Then you will have gravitation amines, and finally on Friday we will have the high weightage chapters. Okay, we will have a high weightage predictable pattern of question paper. As always, Friday, Saturday we do this, right? You all know that. Chalo. Now everybody, let us start with our periodic table, the story of the periodic table. As we all know, the periodic table actually started long back, isn't it? Yes. So initially what we had was Doberener's triads, and even before that we did not even have to classify the elements because there were very little elements, right? There were very little elements and you don't really need to classify it. When do we start classifying? When do we start grouping things? When there are more numbers, right? And that's when it is not easier to study each and every element, but it is easier to study the properties when we study them as a block, right? And that is why we need the periodic classification. So initially it started with Doberener's triads, then came Newland's law of octaves, then came Lothar-Mayer's curve, and then came Mendeleev's periodic law. And at that time we know that the properties of the elements are a periodic function of their atomic weights. That was the principle of Mendeleev's periodic table. However, the actual milestone was brought to you by Henry Moseley, everybody. And as you say, he observed regularities in the characteristic of X-ray spectra of elements and he plotted a graph, everybody. Can you all see the graph? Right here, this is the graph, everybody, and he plotted a graph against, as you all can see, here is Z. Z is the atomic number and this is root over nu, which was the frequency of X-ray, everyone. When he plotted the graph, he saw that, my goodness, this was a straight line. And when you get a straight line? When things are proportional to each other, right? And to make the matter more interesting, he plotted the graph, the same exact graph with also atomic weight. But at that time, he found a zigzag line. That means that atomic weight is not the picture changing factor. It is the atomic number, right? It is the atomic number. So he used the atomic number and that's when he stated, everybody, he said that the properties of elements are the periodic function of their atomic numbers and not atomic weight. So from here we have the modern periodic table and this is what we have to study. This is included in our syllabus. However, the older part, the classical physics, the classical periodic table is not included, so forget about it. But I had to tell you the story because that is the story, right? Now we know that the periodic repetition due to similar valence shell electronic configuration after certain regular interval is seen, and we know that atomic number is basically equal to number of electrons in neutral atom, or it is equal to number of protons, right everyone? Now when we look at the periodic table, this is our most famous, the very pretty looking periodic table. And right here in this periodic table, we can see this is the S block, these two, this is S1, S block 1, group 1, and this is S block group 2, right? Now, if you count all of these, you will find 13 elements, including hydrogen. However, let me tell you that hydrogen is actually not a part of the S block elements. When we study S block elements, we do not study hydrogen. If you remember, you had S block and hydrogen, two different chapters. Remember that? Yes. Why so? Because hydrogen actually does not have a place in periodic table. And if any of you who are watching this session, if you can find the place for hydrogen, guess what? You will actually get a Nobel Prize. Maybe, maybe. Anyway, yes, so I was telling you this interesting fact. Here you can see that this is your P block, right here at the center this is your D block, and right here is your F block. We have pushed them out. Why? Because I told you in Instagram, what do we do? Aesthetically sensitive. We want things to look pretty, and see, now it looks pretty, isn't it? Yes. Imagine if this was also inside it, this whole shape and size of the periodic table would have looked very topsy-turvy and won't look nice, right? It would look chaotic. Now it looks so nice, see? Colorful and pretty. That's why. That's actually the reason. That is actually the reason. The reason why F block is not included in the periodic table itself, although they are inner transition elements and all of them belong to this group 3. Why do we not include them? Just so that the shape and the size of the periodic table is not disrupted, truly. Anyway, now everybody, if you remember, the S block, the S orbital can hold 2 electrons, and you can see that there are 2 groups here in the S block. In the P block, we all know that there are 6 electrons that the P block or the P orbital can hold, and hence in the P block you will see 6 groups. See, 1, 2, 3, 4, 5 and 6 right here. This is your noble gases, right? So they are your P or P block. And here in the D orbital, we know that you can hold 10 electrons. So here there are 10 groups, everybody. And finally in the F orbital, there are 14 electrons. And if you count it, you will have here 14 number of elements. Okay. All right, everybody. So this is basic gist of the periodic table also. One more thing is, in this part, in the S block, you will find all metals. In the D block, you will find all metals. In the F block, there are all metals. In the P block, you will also have metals such as aluminium, gallium, indium, thallium, lead, tin, bismuth, polonium. These are all metals. However, you also have something that is called as metalloids. And who are these metalloids? You have goats are silly aunties. Goats are silly aunties. These are your metalloids, that is germanium, arsenic, selenium, antimony and tellurium. Goats are silly aunties. Please do remember, these are the only metalloids, everybody. And like I already told you, don't argue with me in the chat box that no ma'am, this and this are also metalloids. No. That's it. These are the only metalloids. Rest all of them are non-metals, and whatever I have just told you right now, these are your metals. Okay. These are your metals. All right. Clear? Okay. Now, let us have a look at our S block elements, everybody. S block elements, let us just study them a little bit more, a little bit better. Now, S block elements, how do you write their electronic configuration? You can write their electronic configuration as NS122, everybody. Yes, because they can only hold 2 electrons. That is the maximum occupancy. So, you will either write it as NS1. If you write it as NS1, that means they all belong to group number 1. And if you write it as NS2, that means they all belong to group number 2, right here, everybody, right here. This beryllium, magnesium, calcium, strontium, right? They all belong to group 2. Okay. All right. So this is how you write down the electronic configuration, the general electronic configuration of all the S block elements, right? The elements of group 1 and group 2, they constitute the S block. The S block elements, they lie on the extreme left hand side of the periodic table, as I just showed you, and the total number of elements including hydrogen, you have 13 elements. Okay, this block has all metals, by the way. Group 1 is called as alkali metals and group 2 is called as alkaline earth metals, right? Okay, great. Now, with that being said, now we are going to move on towards the P block elements. The S and the P block elements together are called as the representative elements. They are the main blocks of this whole P block. The D block is called as the transition block. Why? The transition elements, because as you move from S or S block to P block, the properties that transition through the transition elements, which is why they are called as transition. F block is called as inner transition elements, right? Very good, great, okay. Now P block, how do you write the electronic configuration? You write it as NS2 NP126, everybody. What do you write? NP126, because it can hold 1 electron, 2 electron, 3, 4, 5 and 6 electrons, right? For boron, it is NS2 NP1. Carbon NS2 NP2. For nitrogen, it is NS2 NP3, right? So so on and so forth. You get the point, correct? Okay. Now, in this case, what happens is the elements in which the shells are up to n-1, they are completely filled, and the differentiating electron enters the p orbital of the nth orbit, correct? Okay. The general electronic configuration, I've already told you, elements of group 13 to 18, they constitute the P block. The P block element, they lie on the extreme right in the periodic table, and the block includes some metals, all non-metals and metalloids, okay? And the total number of elements in this block is 37, okay? All right, cool, got it, great. Now we are moving on towards the D block elements, everybody. In the D block elements, there are now the electronic configuration that you write for D block, there is a slight twist. How do you write it? You write it as NS2 and then you write N-1 D1 to 10. Alright, this is your electronic configuration. For example, scandium is NS2, that is 4s2 3d1. For titanium, 3d2 4s2. For vanadium, 4s2 3d3. However you want to write it, because there is a ultimate shell and there is penultimate shell. Now what do we mean by this? For example, if this is my nucleus here, let's say this is my nucleus, this is the shell, this is the shell, this is the shell. This last shell is called as the ultimate shell, right? The last shell is called as the ultimate shell, and here this shell is called as the penultimate shell. Okay, this is called as the penultimate shell. All right, everybody? Yes. Now the elements of group 3 to 12, they constitute the D block, and here the exceptional element is your palladium. Now palladium has a configuration of 4d10 5s0. It does not have 5s2 4d8. It has 4d10 5s2. All right, this exception, there are also certain other elements which are exceptional, and that I have taught you in the lesson coordination compound and DNF block that I have taken very recently, and it is a good revision. Please go and watch that session. I mean, I can tell you right now, but I will still suggest that please go and watch that session, because with all the exception, this thing about palladium will also get cleared. Okay, all right, everybody. Now moving on, the D block elements, it has 4 series. There is first, second, third and fourth. The first series is called as the 3D series, and it starts from scandium, goes up to zinc. Okay, that's called as the 3D series. The 4D series is from yttrium to cadmium. The third series, that is the 5D series, starts from lanthanum and goes up to mercury, and the fourth series, that is the 6D series, it starts from 89 atomic number actinium and goes up to 112 Cn. Okay, all right, these are the series that you have in your D block elements, and we all know that the D block elements, they include zinc, mercury and cadmium. However, they are not termed as transition elements. And why so? Because one major important definition of transition elements is that the transition elements, they have partially filled d orbitals, either in their atomic state or in their simple ionic forms. That is the key word in the definition, everybody. Either in their atomic form or in their simple ionic form, they have a partially filled d orbital. However, that is not the case with zinc, cadmium and mercury. They have only fully filled d orbital, they always have d10, d10, d10 configuration, and hence they are not called as transition elements. However, we do study them with the d block elements because they are included in the d block elements, but they are not transition elements. Please do remember it. Okay, this is important. Chalo, all right. Now everybody, finally we reach the F block elements, and here when we are writing the electronic configuration, my dear bachu, so we will write it as ns2, then we write it as n minus 1 d1 or 0, yes, and finally you write n minus 2 f to the power 1 to 14. Okay, yes, it is f1 to 14. Chalo, let me write this a little better. Let me not write it here. You will write it as n minus 2 f to the power 1 to 14 because f can hold on to 14 electrons. So this is your general electronic configuration. Remember that all the F block elements, they all belong to the third group, that is they fall in the scandium group. Their leaders are lanthanum and actinum, yes, and that is why they are called as lanthanoids and actinoids. All right, yes, they are called as the inner transition elements because they are inside the transition element, but like I said, we want our periodic table to look pretty, hence we have pushed them outside the periodic table. Correct? Great. Okay, good. Got it. Now you might get certain questions such as what is predict the period or predict the group or predict the block of this element that we have not discovered yet. These kind of questions do come, so please pay attention. How will you figure out the period of an element? If you want to figure out the period of an element, you will correspond that to the principal quantum number. Principal quantum number bole to the n that we were writing, this n is n denotes the principal quantum number. All right, and that is your period. What is period? Period is the horizontal lines. Yes, when you are coming from scandium to zinc, yes, when you are coming from yttrium to cadmium, yes, that is called these are called as period, and top to bottom is called as your group. So you have 18 groups but 7 periods. Okay, cool. All right, now how do we figure out the block of an element? The block of an element, what you are going to do is, it corresponds to the type of subshell which receives the last electron. Wherever the last electron goes, if the last electron goes to D, then it is a D block element. If the last electron goes to P, then it is a P block element. If the last electron goes to S, then it is a S block element. Okay, and finally when we come to the group, how do we calculate the group? If it is for S block element, then the group number is number of valence electron. If the valence electron is 1, then it is group 1. If it is 2, then it is group 2, that is alkaline earth metal. Okay, for P block elements, how do you calculate the group? Okay, for P block element, 10 plus number of valence electrons, that is the last, let's say that it is 3s2 3p3, so 2 plus 3 is 5. Now 5 plus 10, if you do, you will find that the element falls in 15th group. Okay, that's how you calculate. I'll show you. Then for D block elements, you will see that the number of electrons in n minus 1d subshell plus the number of electrons in valence shell means that it belongs to the D block elements. Got it clear? Now let us solve a question, everybody. The question is, the atomic number of element is 33. Where will you place the element? Okay, let us do that. Let us do that. Shall we do that? Yeah. So the question is that 33 is the element's atomic number, right? So how are we going to solve it? We will write down the electronic configuration, that is 1s2, 2s2, 2p6, 3s2, 3p6, then we have 4s2. So 10, 10, then we will have 3d10, 30, and then finally it will be 4p3, isn't it? 4p3, right? 4p3 is the last shell. Now 4p3 and there is 4s2. So 2 plus 3 is how much? 5. Now 5 plus 5 plus 10 we have to do because we can see that it is p orbital, and that means that it will be 15th group, bachos. Yes, the correct answer is 15th group. That means option number C is the correct answer. Quick, all right? Quickly write down some EPBT in the chat box if you were able to solve it, everybody. Now moving on from this, let us have a look at a JEE Mains 2019 question. That means this is the previous year question, everybody. And the question is, the element with Z is equal to 120. It has not been discovered yet. where will you put this? Okay, where will you put this? Now we know that, what do we know? We know that 118 is the last element, that is oganescent, Og. Og is a noble gas, okay? Og is a noble gas and it belongs to obviously the 18th group. If it is going into the 18th group, that means we have to start from 119 will be in group 1, 120 will be in group 2, and group 2 bole to alkaline earth metal. Yes, alkaline earth metal is your correct answer. Alkaline earth metal is the correct answer. Very, very, very good. Chalo. Next, everybody. Next question is the group number, number of valence electrons and the valency of an element with atomic number 15 respectively are. So how do we write the electronic configuration for 15? Atomic number, we will write it as 1s2, 2s2, 2p6, 3s2 and 3p3. So from here clearly it is belonging to the p orbital, and 3 plus 2 is 5, 5 plus 10 is group number 15. If it is group number 15, group number is 15 here, okay? Now here we can clearly see 2 plus 3 is 5. So valence electron, everybody, is, we can say valence electron is equal to 5. But what is the valency? Valency is 8 minus 5 is equal to 8 minus 5 is equal to 3. That means 15, 5, 3. Option A is the correct answer, okay? Option A is the correct answer. Clear, guys? Yes, EPBT? Great. Now we are moving into something that is called as atomic radius, and we have to follow the trend of atomic radius, okay? What is atomic radius? Atomic radius in its most basic fundamental form is the distance between the nucleus and the outermost shell, that is electron. That's called as atomic radius. Now there are three different types of atomic radius. What do you have? You have covalent radius, you have metallic radius, and you have van der Waal radius. Now this van der Waal radius, it is solved or it is calculated for those gases or those elements which are not bonded, okay? For example, noble gases. We all know that noble gases, they are monoatomic, right? They do not exist as diatomic gases like N2, O2, H2. No, they don't exist like that. They are helium He, xenon Xe, radon Rn, right? They exist like this. So that means, everybody, so I have a the next door building, I think somebody is using the washing machine, and oh my god, what a crazy washing machine. It makes so much sound. Anyway, that's why I got distracted. Anyway, guys, coming back to it. So van der Waal radius is calculated for noble gases, those which do not bond. And that means that this atom and the second atom, they are not bonded actually. They have a gap between them. They are adjacent. That means that this atom and this atom, they're not bonded, but they're just adjacent, just existing, just existing right there. So in between them, you will calculate the internuclear distance and then just divide it by 2, and that, my dear student, will be your van der Waal force or the van der Waal radius. Here, van der Waal radius. The van der Waal radius is going to be greater than the metallic and the covalent radius, because here we are talking about a case where the atoms are not even bonded. They are far away from each other. So obviously it is going to be greater. Now we talk about metallic radius. Metallic radius, where will you see it? In metals, obviously, right? Yes. And it is 1/2 of the distance between the nucleus of two adjacent metal atoms. Two adjacent metal atoms. The metal atoms are side by side each other. You calculate the internuclear distance and just divide it by 2, and that will give you your metallic radius. All right? Yes. And finally, here we have the covalent radius. The covalent radius is the internuclear distance between two covalently bonded atoms. That means that, let's say that here you have an atom, here you have another atom, these two are bonded. This is the nucleus here, this is the nucleus here. You will calculate the distance between these two nucleus, which will be called as your internuclear distance, right? What is it called as? It is called as internuclear distance. And then you will just divide it by 2, and that will give you your covalent radius. So ideally, generally, we have noticed that covalent radius is the smallest, then you have metallic radius, and then finally you have the van der Waal radius. It is the largest among the 3 atomic radius. Cool? Okay. Now what is the trend? How does atomic radii vary? Atomic radii can vary 2 ways. One, left to right in a period, and one is top to bottom. left to right, when we move, we see that the atomic radii decreases. Now you will think that, but ma'am, how is this happening? The atomic number is increasing. If the atomic number is increasing, that means there are more protons, more electron. Ideally, it should increase. By why is that happening? Actually, you know what? Atomic radii depends on two factors. Number one is your nuclear charge. Yes. How much charge does the nucleus have? And number two is the screening effect. Now, what is the screening effect? My dear students, now you can see my face. Now you can see my face, but now you cannot. This is called a screening effect. See, now you cannot see my face. Can you see my face? No, you can only see the iPad. So this is called as your screening effect. But if I wear the glasses, which I did show you the example even in the live class. But now if I wear my glasses, you can clearly see my face and you can still see my eyes, right? So this does not have any screening effect, but it still is a screen. It is a screen, however, because of the glass which is transparent, I can say that it does not have any screening effect because the light is hitting my eyes. You can see my eyes. So there is no screening effect, right? Getting my point? So every orbital, such as the s orbital, the p orbital, the d orbital, the f orbital, they have their own set of screening effect. The s orbital, because it is completely spherical in nature, it has the highest screening effect. The p orbital though, my dear students, the p orbital though, everybody, we all know that the p orbital looks like this, the it is a dumbbell shape, right? So this is your nucleus, let's say. The center point, this is your nucleus. And let us just say that here is your electron. So if the nucleus can, to Mary, it can see the electron and it can pull it closer. Can it not? Yes, absolutely. And a little similar to this, you also have the d orbital, which has double dumbbell shape. Now imagine if the electron is here, 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 it can always see and see the electrons, right? The nucleus can easily see the electron and the nucleus can catch hold of the electron. So they have very bad screening effect. What do you say? They have very bad screening effect, and which is why the atomic radii decreases when we have a look at the d block elements or the f block elements, right? Now when you move from left to right in a period, your principal quantum number remains the same. There is not an increase in the shell. The shells remain the same. The principal quantum number is same. You are only increasing the number of electrons or the number of protons for that matter, right? Now, if you increase the number of protons, what happens is your nuclear charge increases. That means there are more protons, more positive charge, and that can pull in more electrons. And hence we see that the S block elements, they have the largest size, but the P block elements, they have comparatively smaller size, except noble gases. Noble gases, because they are not even bonded, they will obviously, you will always measure the van der Waals radius and they will have the largest size. But otherwise, S block elements, the group 1 elements, they have the largest size, everybody, in the whole period. And as you go down, as you move on and on, till the group 17, you will see that fluorine has the smallest size, right? Why so? The effective nuclear charge increased from left to right. And what is effective nuclear charge? Nuclear charge, you understand. What is effective nuclear charge? Effective nuclear charge is how much charge the last electron from the nucleus effectively is experiencing. That is your effective nuclear charge. Got it? Yes. So we understand why left to right, as you move from left to right in a period, what is happening? The atomic size decreases. But as you move from top to bottom, the atomic size increases because now you are increasing the principal quantum number. And as you increase the principal quantum number, you are increasing the shells. As you increase the shells, what will happen? The atomic radius will start increasing. Correct? Yes. So top to bottom increases, left to right decreases. Got it? Clear? Now here, let us talk about a mystery. Now we want to increase, or we want to see a decrease in the size as we move from left to right, but we do not see that in the case of the first transition series, that is from scandium to zinc. When we move, we see that initially what happens is the atomic radii decreases, then it remains constant for some time, and then it increases again. Because now I just told you that atomic radii depends on two factors, that is one, screening effect, second, nuclear charge. So initially when it is decreasing, you understand that it decreases because of increase in nuclear charge. When you are increasing the nuclear charge, see, scandium is 21, titanium is 22, vanadium is 23, chromium is 24. So you understand that you are increasing the atomic number, that means number of protons increases. Number of protons increases bole to nuclear charge will increase, and if nuclear charge increases, that means that there will be a decrease in the atomic size, and that is exactly what we are seeing. Now here what happens is the screening effect and the nuclear charge, they are compensated well, and here you see a twist that they almost remain the same. For manganese, iron, cobalt and nickel, they are of nearly same size because the screening effect and the nuclear charge, they are well compensated by each other. Correct? Got it? And finally, when we reach the when we reach copper and zinc, we see that there is an increase in the atomic radii. Why? Because now the screening effect has increased. When the screening effect increases, sorry, the screening effect has decreased. Yeah, the screening effect has decreased. If the screening effect decreases, atomic radii increases. Yeah, screening effect increases, atomic radii. Am I saying it ulta? One second. If the screening effect decreases, atomic radii decreases. No, screening effect is directly proportional to atomic radii. Yes. So if the screening effect increases, the atomic radii will increases. Here what is happening is the screening effect has increased. And because of the increase in the screening effect here, the atomic radii also increases. That is why we see this trend in the atomic radii. Okay. Now that's not it. We have another mystery here. Now, as we move from top to bottom, we expect the atomic radii to increase. However, we see that in the boron family, Bal Gangadhar Indian Tilak and neonium. This is neonium. Neonium is radioactive. Okay. Neonium is a radioactive element. We do not study about it more, but I think that in your new NCRT you do have they have observed and they have noted these new elements as well. So I'm just letting you know neonium is the new element, right? So what happens here is you would expect that as you are moving from top to bottom, it increases. However, here, right here, everybody, we see a twist. What do we see? We see a twist here. We are expecting that aluminium will have a smaller size than gallium. However, the twist is that gallium has a smaller size than aluminium. Why so? Why so? Achha, what happens? Let's say that you were expecting that when you go, there will be less people and you will be able to meet just your close friend. But let's just say that your parents or somebody threw a surprise birthday party and there are lots of people in the room. What will you do? You will just enter the room and you'll be all shy, isn't it? And you'll be like, I don't want to talk. You will sit in a corner. So you go all small, right? You go all small. You're feeling very shy. You sit in a corner. Similarly, everybody, gallium, the gallium was expecting that, oh, my atomic radius is going to be big, big, big. But then just before gallium, for the first time ever, you have introduced the D block elements. And there are tens of D block elements that are right before gallium. So what will gallium do? Pichik. It will reduce its size. But that's not the that's not the law of nature. The law of nature here is the d orbitals, they have a stupid shielding effect. They have a very bad shielding effect. The d orbitals, there are enough space for the nucleus to look at the electron and pull it back to its, and pull it back into this force field, right? So what happens is the d, because of the introduction of the d orbitals or because of the introduction of the d block elements, gallium has a smaller size. Do we understand this? Do we understand this? Yes. Now moving on here, let us have a look at it. Once again here, in case of the 3D series, 4D series and 5D series, we were expecting that the atomic size will increase, right? But that's not the case. We see that from 3D to 4D, yes, it increases, but from 4D to 5D, it does not really increase. It is almost the same. Why? Because right here at the 5D series, just before lanthanum or just inside lanthanum, we have introduced the F block elements. And the F block elements, the F orbitals, they have even worse, the worst kind of shielding effect. It's like you have built a glass house. If you build a glass house, everybody can see what you are doing inside the house, isn't it? And you will have to spend more money to get all those blackout curtains and maybe paint the house somewhat, or maybe you have to hide somewhere and go, isn't it? Do you understand it? So the F orbitals are sort of like that. They're like glass house. You can see everything that is happening. Wherever the electron are, the nucleus can see it, and the nucleus can pull it back into its field of force. It can pull it back. And that is why here there is a decrease in the radii, and this is called as the effect, the consequences of lanthanoid contraction that you see in zirconium, hafnium, niobium, tantalum, molybdenum, tungsten, technetium and rhenium. You also see it in ruthenium and osmium. You also see it in rhodium and iridium, and you see that all of them, they have comparable sizes only because of the introduction of the 4f introduction of the uh, F block elements. Got it clear? Yes. Can I have some EPBT, guys? Easy peasy biryani tasty in the chat box. Do write it down. Now we are going to understand the ionic radii. What is ionic radii? What is ion? What is ionization? Ionization, from ionization, the end product that you will get is always ions, my bachos. Okay, it is always going to be ions. Right. For example, if you take NaCl, solid form of NaCl, and if you dissolve it in water, what will you get? Na plus Cl minus. So when an atom has gained electron, what has it gained? When it has gained electron, what exactly is it gaining? It is gaining the negative charges, because we know electrons are negatively charged, right? Yes. So when it is gaining electrons, it is gaining negatively charged particles. That means that more negative charge is hovering on its head. That means that the atom has acquired, it has attained what, Moksha? No, it has attained negative electron, right? Negative charge. So it will be called as what? What will you call it? It will be called as an anion. Okay, it will be called as an anion. But when the electron is losing electron, what did I say? When the atom is losing electron, then what will happen? It is losing the negative charge. That means right now it has more positive charge. So it will have a positive charge on its head that will be hovering around, and at that time we call that to be a cation. What do we call it? A cation. Okay. Now tell me something. Very, very, very common sense question, everybody. So if an ion is cation, that means it has positive charge. Positive charge means there are more number of protons. More number of proton means Z effective. Nuclear charge is more. If nuclear charge is more, the electrons will be pulled closer. And what will happen to the ionic radii? It will be small. Yes, it will be smaller. So the size of the cation is always going to be smaller than the atom, but the size of the anion, because now there are more number of electrons, and that much the proton cannot control. Imagine, understand this, everybody. If I had 10,000 students in my class, do you think just me will I be able to, one teacher will be able to handle 10,000 students? Very difficult. Similarly, if the protons, number of protons, let's say, are only 6, but number of electrons are 10, 6 protons will not be able to handle those 10 electrons. For 6 protons, it will be very hard to handle 10 electrons, and that is when the size increases. So an anion size will be bigger than the atomic size always. Do we understand this, everybody? Do we understand this, guys? Now just read it. The distance between the nucleus and the outermost electron of the ion. The ionic radii can be estimated by measuring the distance between the cations and the anions in the ionic crystals. That's how you measure it. The radius of the cation is always smaller than their present atom, and the anion is larger than their parent atom. Got it clear? Yes? Okay. All right, everybody. Now, from this case, we have certain question. We also come across something that is called as isoelectronic species. And please pay attention, isoelectronic species is NT's favorite topic. They always usually ask you one question from isoelectronic species. And I will give you some some similar questions as well. So the species that has the same number of electrons but difference in the magnitude of the nuclear charge. Like, hey, you understand, right? What did I tell you? The parent atom and the ions will have the same number of protons. You cannot change the number of protons, can you? No. So the number of protons remain the same, but the electrons are fluctuating. Electrons can be more, electrons can be less. If it is less, atomic radii decreases. If it is more, atomic radii increases. So yes, now that means that the magnitude of the nuclear charge will be different, right? But the number of electrons are same in all of these species. Hence we call them isoelectronic species. Now for example, have a look. N2 minus, N2, no, N3 minus. Nitrogen 3 minus, that means 3 electrons are added. So 10. Atomic number of nitrogen is 7, but here number of electron is 10. For oxygen, atomic number is 8, O2 minus, that means 10. For fluorine, atomic number is 9, but how many number of electrons now? F minus, 1 electron extra, so 10. Yes, now if we look at it, neon has what? Atomic number 10. Neon is a neutral atom right here, so there is no addition, no subtraction, and there will be 10 number of electrons. For sodium, 11 is the atomic number, but since we have written it as Na plus, that means that it will have 10 electron plus means 1 electron is less. Now for magnesium has an atomic number 12. It has an atomic number 12, but how many number of electrons? 2 plus, that means 2 electrons you have taken away, so 10. For Al, aluminium, 13 is the atomic number, but 3 plus 3 electrons you have taken away, so it will have 10 electrons. Now all of them are isoelectronic species. But look at the Z effective, guys. Z effective, the effective nuclear charge for all of them is different. Do you see? Do you see, everybody? Yes. And that means that the sizes of them will also differ. Okay, the sizes of them will also differ, and you will see that Al3 plus will be the smallest, then will be Mg2 plus, then it will be Na plus, then it will be neon, then it will be F minus, O2 minus, and N3 minus. N3 minus actually will have the highest charge or highest radius, although it has only 7 protons. It has 7 protons, but now it has 10 electrons. And 3 minus, there are more number of electrons. The proton will not be able to handle its size increases. Yes. Cool. Let us solve a question, everybody. Let us solve a question. Now tell me, which of the following has the largest radius? Which of the following has the largest radius, everybody? Is it 1 is to 2 is to 2p6 3 is to? Is it 1 is to 2 is to 2p6 3 is to 3p1? Is it 1 is to 2 is to 2p6 3 is to 3p2? Or is it 1 is to 2 is to 2p6 3 is to 3p3? You tell me. Which one? Which one, guys? What do you think? What do you think? I think that the largest radius will be of 1s2, 2s2, 2p6 and 3s2, 3p2. Yes. Yes. That will have the largest radius. No, sorry, no, not 3p2, 3s2. 3s2 will have the largest radius. Why? Because right here what will happen is, as we go, like now for 3s2, 3p1, 3p2, 3p3, what will happen is Z effective, the effective nuclear charge will keep increasing, and hence the atomic radii will decrease. However, for 3s2, that is option A, it will be the largest. Z effective is less here. Why? Because number of protons are less. Number of protons are less. That means the protons will not be able to handle the electrons. Got it? Clear? Yes? Okay. Let us move on to the next question, everybody. And the next question is, correct order of radius of elements is COFClBr. Which one will have the largest radius and which one will have the lowest radius? Now we all know that fluorine will definitely have the lowest. BCNOF, right? So fluorine, then it will be oxygen, then it will be carbon, then it will be chlorine, and then it will be bromine, because top to bottom will also act, right? And that means that I think it is option, is it option A? Please check it out, guys. I think it is option A, right? Yeah? Okay, great. Option A, done. Next question. The increasing order of the ionic radii of the given isoelectronic species A. Let's have a look at it, everybody. These are isoelectronic species, everybody. So from here we all know that whichever has the highest positive charge, that will be the smallest, and we all can see that Ca2 plus, Ca2 plus has the highest positive charge, so that will be lowest, then it will be Ka plus, then it will be Cl minus, and then it will be S2 minus. S2 minus will have the biggest radius. Why? Because more number of electrons than proton, and that means that option C is our correct answer, right? Option C is our correct answer. All right, everybody. Now we come to another trend, that is ionization enthalpy. So let's understand what is this ionization enthalpy, everybody. Ionization enthalpy, as we all know, is the amount of energy that you have to give an atom to take away its electron. I have used the same example, and once again I'm going to tell you the same story, everybody, because I believe that it is the most effective one. We all shop, right? And especially me being a girl, I mean, we love shopping. Who can say no to it, right? We all love shopping. So what do we do when I want to shop something? I have to give these online websites, right? Myntra, Ajio, Amazon, whatever it is, I have to give some money to them to be able to get the shopping, right? Whatever I want to buy, I might want to buy jeans, I might want to buy a coat, I might want to buy a sweater, whatever I want to buy, they are not going to give it to me free of cost, right? Are they? How will they make profit then? No, right? The law of universe, you need profit, everybody needs profit. So anyway, so here what is happening is I have to give them a little bit of money, or certain amount I have to give them. I have to give some amount of money to be able to get that product. So what am I doing? I have to give some currency. What is the currency? When we are talking about atom, the currency is, what is money, money? Money, money here is energy. Atom understands money, money as energy. They do not understand money, they understand energy. So the atom will need energy to be able to release that electron. Otherwise, it will not be able to. You have to give it something to be able to take that electron. And that is called as ionization energy, when you are giving some energy to take away one electron from the isolated gaseous atom. Now chemistry, I can't say that just like how Nabamita Ma'am likes shopping and she has to give some money to Mintra to be able to get the jeans, you will write that over. No. The definition is going to be a little chemistry oriented, and you will write that the required energy to remove an electron from where? How will you remove it? If the atom is bonded, you will take away one electron and run away, or what? No, you cannot do that. First, you will have to break the bond. You break the bond, then you take it to isolated gaseous state, because isolated gaseous state, when it is a gas and it is alone, only that time you can take away the electron. You getting my point? Aren't you? Yes, exactly. Exactly. That is why, your parents won't leave you alone. Why? Because if they leave you alone, you will go spend all money and come. If you are with them, you will spend less money. That is why. Yes, if you are alone, if you are in an isolated gaseous state, what will happen? You will be like, yeah, your pantaloon so nice, or lifestyle so nice, or van using so nice. You will buy everything and you will come back and you will lose all money. And that is why atoms also like to stay bonded. They don't want to give away so much electron, yeah, so much energy. Why do they need to do that? Exactly. That's your ionization energy. Now, okay. Now, first time I make that mistake of losing all my money, right? I can do that first time. Then I come home, my mom will scold me. Second time, if you ask me to spend all my money, I'll be like, no, yeah, I will save some money. Yeah, I'll save some money. Yeah. Let me not do that. I'll save some money. Yeah, I'll do that, right? Third time, it will be even more difficult because my mom would have scolded me again, right? Yes, similarly, when these atoms, when you have to take away the first electron, they will give it to you. Simply, they will give it to you. With less energy also, they will give it to you. Second time, now they are like, hey, Poda, not gonna give you the second electron. They will not give you the second electron. So you will have to spend more energy. You will have to give them more energy to be able to take away that electron. And the third time, it will be even harder for you to take away that electron. That means that you will have to give more energy to take away the third electron. Now hence we see that there is a steady increase from the first ionization energy to the second, from second to the third, the ionization energy increases, because the atoms, they do not like to give away their electron just for the simple sake of your joy. They don't like it. Okay, getting my point? Yes. Now what happens is, what we have seen is, as the size increases, ionization energy decreases. Why so? Let's understand this better. Okay. All right. Imagine if you have a joint family. If you're living in a joint family, and let's say that you want to go to shopping, what will you do? Uncle, I'm going for shopping. Auntie, I'm going for shopping. Sarita auntie, I'm going for shopping. Mama, I'm going for shopping. Grandma, I'll go. Will you actually tell everybody and then go? No. When you are in a joint family, it might get a little easier for you to go out because everybody is not noticing you. It's a big house. People are busy with different things, and you will be like, Mama, I'm leaving. Okay, bye. You will go. It's easier. It's easier, right? But if it is a neutral family, just mom, dad, and you'll be like, Mama, please let me go. No, Papa is not giving information. Papa is not giving me permission. Then you go to Papa. Papa, please let me go. No, Mama has already said yes, but Mama has still not said. So again, you will have to go. You keep doing this. Just go to, like, mom and your dad, mom and your dad, and finally after 3 or 4 days you are able to coax them and cajole them, and finally they are like, okay beta, go. By that time your sale is over, you can't shop now. You getting? Just kidding. Understand it by stories. You will remember it. So here what happens when the size increases, ionization enthalpy decreases. That means it is easier for you to take away the electron. As the size of the radius is big, the electron is far away from the nucleus. Now the nucleus, effective nuclear charge has a decrease because the nucleus is far away from the electron. The nucleus is not able to see the electron, and the electron you can take it away and run. But if the atom is small, now the nucleus is able to see the electron. It will not allow you to take away electrons so easily. It will want you to put in more energy, more energy, more energy, and only then it will be like, okay, you seem to like my electron a lot, I will give you blessings. Right? Then only it will do that. Getting my point? Yes. But if the Z effective increases, as the number of protons increases, that means the size decreases, ionization enthalpy increases. For fluorine, you cannot take away the electron here. Fluorine will not give away the electron so easily. Fluorine will be like, hey, what are you doing? I already have a small size here. I have my enough electrons that I really like, and you want to take away that electron also. How will I maintain my stability? Fluorine will not give you that. But as you go down, fluorine, chlorine, bromine, iodine, right? Astatine will be like, bhai, I have such a huge size of atom. You know what? You take away 1, 2 electrons also you take away. No problem. You take it away. Astatine might. You getting my point? Yes, everybody? Clear? Now, for electronic configuration, let's talk about this. Yes, for a stable electronic configuration, especially when you have a half filled or a fully filled electronic configuration, that is P3, P6, D5, D10, NS2. Yes, in these scenarios, you will see that the ionization enthalpy is even more. Why? Because they have the stability, na Baba? They have the stability. Are you getting my point? For example, understand this, okay? Let me give you an adult explanation here, okay? Adult explanation. Imagine that I want to buy a car. The car costs 10 lakh rupees. Now I have already saved 5 lakh rupees. If I have saved 5 lakh rupees, and if any of my friend, they come and tell me that, Nabamita, could you please give us 1.5 lakh? I will return it back after 2 months. By 2 months, how will I be able to save? What if by 2 months my car is not there, only I will have to wait for even more time? I will not give, because half filled. No, 5 lakh I have already filled. 5 lakh is half of the amount. I can give it as a down payment. My car can come today, or tomorrow my car can come. Understanding? Yes. Now I do not want to pay down payment, which is what, 3.5 lakh. No, I don't want to do that. Why would I do that? If I pay half, I will have to use less loan. Correct, understanding. So I don't want to give away the money. I'll be like, bro, you understand, no? I'm saving up for money. I'm saving up for the car. Today I won't be able to give you because I have to get the car today only. Half it. But if I had 2 lakh, and if at that point of time my friend would have asked that, Nabamita, can you give me 1.5 lakh rupees? I have to get something. It's an emergency. I'll be like, sure. Take it. Why? Because I have only 2 lakh. if it takes away 1.5 lakh, it doesn't matter to me so much. And he's telling me, no, he will give me in 2 months. Maybe in 2 months, I will also be able to save 3 lakhs and then I will be able to get the car. But 2 lakh is not enough for the down payment. Let's just say, assuming that it is not enough, it's actually enough, you can get the car, but yeah, assuming that it's not enough, so I will wait. I will wait. Are you getting my point? Similarly, when P3 and P6 or D5 and D10 is there, they do not want to give away the electron because they have a fully filled or half filled stability. Alright? Yes? Okay? Got it? Clear? Okay. Now guys, we understand that penetration effect of the electron. An electron will experience the greatest effective nuclear charge when it is in s orbital than in p orbital. If the electron is in s orbital, it will have higher penetration effect, and if it is in p orbital, it will have a lesser penetration effect. And then, as you know, the d and the f will have even worse penetration effect, right? Yes, understanding everybody what is what? Great. EPBT, hashtag EPBT, great. Okay. Now, when we move from left to right, we see that the ionization enthalpy increases. Why so? Remember, what was happening? It is inversely proportional to atomic radii, everybody. Atomic radii increases, Z effective, atomic radii increases, ionization enthalpy decreases. So that means that when you move from left to right, you know that the size is decreasing. Radius is decreasing. If radius is decreasing, that means ionization enthalpy will increase. And if you move from top to bottom, then what is happening? Atomic size is increasing. If it is increasing, then ionization enthalpy will decrease. Yes, and that's it. That's it, everybody. That's it. Okay? Alright. Yes, so are we clear with this? Now here we see that there is an exception in case of nitrogen. Nitrogen has higher ionization enthalpy than oxygen. Why so? Because nitrogen has a stable half-filled electronic configuration, which is 2s2 2p3, my dear students, 2p3. And we know that p orbitals can have 6 electrons. They can hold on to 6 electrons, but right here you have 3 electrons, which is half-filled. So the half-filled p orbital shows a stable state and it does not want to give away the electron, hence the ionization energy increases. In case of beryllium and boron also you see the same. Boron has a lower ionization enthalpy than beryllium. Why so? Because beryllium has a fully filled s orbital, that is ns2. It has 2s2 electronic configuration. It is fully filled, agree, because s orbital can hold only 2 electrons. So only 2 electrons, it is fully filled, more stability, it will not want to give away electron, and hence we see that the actual ionization enthalpy trend is lithium, then boron, then beryllium, then carbon, then oxygen, then nitrogen, then fluorine, and then neon. So the twist is beryllium and boron and oxygen and nitrogen. Okay, this is the exception right here. Now, we also see that ionization energy, there is a twist in case of the Bal Gangadhar Indian Tilak neonium and the chemistry sir gives snappy problem. What was the name? Flerovium. Flerovium or something like that. FL. This is FL, okay? It's not fluorine. It is flerovium or flerovium, flerovium only. I think it is flerovium. Could you please check and let me know the name in the comment section? Okay, let me know the name in the comment section. I've forgotten, but I think it is something like this. Flerovium, flavium, something like that only. Can't remember. Can't remember. You can check it and tell me. Yeah, the name anyway does not matter. Nobody is going to ask you. But anyway, where is the exception? The exception is right here, everybody. We see that the ionization enthalpy of gallium is more than aluminium. Why? Because remember, d orbitals, the d block elements were introduced just before gallium. Gallium has smaller atomic radius. That means that more ionization enthalpy than aluminium. And here, in this case, you see that lead. What happens to lead? Lead, just before lead, you have seen the 4f electrons, the 4f elements, they have been introduced. F orbitals, they have very bad shielding effect. That means that plumbum, lead has a lower atomic radius. If it has lower atomic radius, that means ionization enthalpy has increased. So we see that tin has higher, or tin has lower ionization enthalpy than lead. Lead has higher ionization enthalpy because atomic radius here is smaller. Okay, cool, everybody, got it? All right, yes. Now for transition elements, we see that generally in a period, we know that ionization enthalpy increases. But the increase is not so great when we are talking about scandium, titanium, vanadium, chromium. Why? Because do you remember, they differ only from each other a little bit. And in case of iron, cobalt, nickel and copper, the value is fairly close. It is almost similar to each other. And then in copper and zinc, it is again increasing. It's the same trend that we have seen in atomic radius as well. Right? No exception here. Once you have understood atomic radius, I believe that you can easily understand ionization enthalpy as well. Now guys, let us solve one or two questions. Okay? Yes, it is question time. The first ionization potential of sodium, magnesium, aluminium and Si are in order. What do you think? What do you think, everybody? What do you think? They are all period 2 elements. All of them belong to the period 2, isn't it? And the ionization potential, we know that it increases across the period. That means that silicon will have the maximum. Silicon will definitely have the maximum, right? And then what will happen is, we know that aluminium will somehow have a lesser ionization enthalpy than even gallium, right? Plus it has one unpaired electron in its highest energy orbital, that is 3p. Aluminium, Bal Gangadhar, right? Bal Gangadhar, and then there you have chemistry sir, then you have nitrogen. So it has only one electron. Aluminium will be easily able to give away its electron, okay? Aluminium will be able to give away its electron easily, but magnesium, however, will be, I think, magnesium won't want to give away its electron, but because it is fully filled, 3s2, right? Yes. And what else? Nitrogen, no, sodium will also definitely give away its electron. Sodium will also definitely give away its electron. So I believe that it is Na, then Mg. Then I guess that magnesium will be greater than aluminium and aluminium will be lesser than silicon. I think it is this, which means that it is option A, maybe. Maybe it is option A. Maybe. Let's check it out. Yeah, it is option A. Very nice. Amazing. Okay. Now guys, we will solve a previous year question. Okay. Which of the following has the highest first ionization energy? Highest first ionization energy. We know that as we go down the group, the ionization energy decreases. And as we move across a period, the ionization energy increases. So if we have potassium, then we have scandium, then we have rubidium, and then we have sodium. So sodium, Helena, and then Helena K rub. So they all belong to the same ionization enthalpy. Rubidium will have least, then it will be potassium, then will be sodium. Sodium will have a high ionization enthalpy. Potassium will be a little less. Scandium, as we go that side, scandium is in the next group. So scandium, I think, will have the highest ionization enthalpy. Maybe. I think that is, yay, it is right. Yes, scandium has the highest first ionization energy. Okay. All right. Next question, everybody. Which of the following represents the correct order of increasing first ionization enthalpy for calcium, barium, sulfur, selenium and argon, everybody? Okay. So now we all know, once again we know that on moving down the group, ionization enthalpy decreases. Ionization enthalpy also increases as we move from left to right, right? Yes. So that means moving down the group, that means barium and barium will be lesser than calcium. Calcium and barium, they belong to the same. And then OS say tepo, OS say. So selenium will have a lesser ionization enthalpy than sulfur, right? Then when we are talking about period, so we see that sulfur will be lesser than argon, of course, right? Because argon is what? A noble gas, right? And calcium will be lesser than selenium. Yes, right? Yes. So that means from here what we understand is that barium is lesser than calcium and calcium is lesser than selenium and selenium is lesser than sulfur and sulfur is lesser than argon. Now what does this correspond to? I think it is option Option C. Am I right, guys? Let me know. Is it option C, everybody? Yes, it is option C. It is option C. Great. Well done. Well done to us, everyone. Pat on our shoulder. Chalo, guys. Next question is, in comparison to boron, beryllium has lesser nuclear charge and lesser first ionization enthalpy, great nuclear charge and lesser first ionization enthalpy, greater nuclear charge and greater first ionization enthalpy, lesser nuclear charge and greater first ionization enthalpy, lesser nuclear charge and greater first ionization enthalpy. Yes, boron, beryllium will have greater first ionization enthalpy because beryllium has a stable, fully filled electronic configuration, not like boron. However, boron has more atomic number, that means it will have more nuclear charge. So yes, I think option D makes sense. Option D is the correct answer. Please let me know, are you also getting the same answer? Everybody, yes? Are we all getting the same answer? Yay, all right, all right. So hashtag EPBT in the chat box, everybody. I want some hashtag EPBT in the chat box. Amazing. Moving on, now we are going to talk about electron affinity. Look at the name, guys. The moment you read the name, I believe you understand what is electron affinity. Electron affinity bole to the love towards the electron. Somebody who wants to catch an electron and bring it to them. That is called as electron affinity, right? So the energy released when an electron is added to an isolated. Once again, everybody, see, there is one example that I think that if I tell you, it will be controversial. So I think I should not be telling you. But yeah, let me make it a little more, little not so scandalous, and then tell me. If you are going out alone, don't you think that it is easier for somebody to maybe for you not to be able to cross the road, or somebody to make a fool out of you? It is easier, right? Because you are younger. You are younger to your parents. But if your parents, your older sibling, or a teacher, somebody is with you, then it is not so easier to make a fool out of you. So when you are keeping an isolated gaseous state here, now what happens is you can also push an electron to it, and you can say that, hey, you take it, you better take that electron. And the atom will be like, yo, I'm so alone, so papa, I will take that electron. It will take the electron, right? So you will have to give less energy. But if you want to push in 2 or 3 electrons, then you will have to give more and more energy. Because now whichever electrons are inside, they will also rebel. They will be like, hey, you think we are a fool or what? Huh? You will keep pushing electron and we will keep taking it. We will not take it. So you understand? So there is also electron affinity. There is also electron gain energy. Just like you have ionization energy, you have electron gain energy. When an atom accepts electron, they release energy. They're like, you know what, I have got some electron. You know what, you take it and go. You take it and go. For example, Ambani ji, Amitabh Bachchan, Salman Khan, Shah Rukh Khan, they all do charity, right? Why you and I, we cannot do charity? Why? Because we don't have so much money. When people have money, they can do charity. They're like, yeah, you have so much money. Yeah, I have like, jute bags and jute bags of money. You take some and go. They will give it to you. I can't give money. How? I don't have like money to run my month or my house. I can't give charity. No? I can't do charity like this. I can't go and donate all my money to an NGO. How will I do it? Then I will only have to sit with them. Right? You understand? You get the point, everybody. Similarly, here also, when you push an electron, there is an energy that is released, and that is called as electron gain enthalpy. Okay? Alright, everybody. Yes, guys. Do we understand this? Just a second. Why is it not moving? It's not moving. Alright, anyway. So I wanted to check what is written here, but yeah, that basically they are meaning that, yes. They are telling you that exactly. They are telling you that this is called as electron gain enthalpy. Now, when it is a minus sign, now here you see that delta Hg is equal to minus Ae minus 5 half. Why is there a minus? The minus sign means that energy is released by the system. Okay, energy is released by the system, and this tells us that this is your electron affinity. Got it? Clear? Okay. Now, what are the factors here and how is the trend of electron affinity? Let's have a look at this. Now, we know that atomic radius. When the atomic radius is small, then what happens? Electron affinity is not so much, right? You get my point. Atomic radius and electron affinity are inversely proportional. That means as you decrease the atomic size, the electron affinity somehow increases, and as you increase the atomic size, electron affinity decreases. Why? So if the size increases, that means that the nucleus will not be able to put in enough positive charge to bring the electron in the atom, right? But if the atomic size, if it is small, then what happens? Electron affinity increases. Why so? Atomic size is less. The nucleus is closer to the electron. The nucleus can see the incoming electron and can pull the electron. However, it's not always the case. We will come to that also. We will come to that also. For example, fluorine. Let me tell you only fluorine. You do not see that in case of fluorine and chlorine. Although fluorine has a smaller size than chlorine, we still see that chlorine has more electron affinity. You know why? Because whatever electrons that fluorine has already, right, they get angry. They get angry. When you're trying to push in an electron, fluorine, the existing electrons are like, hey, you think we are foolish or what, huh? You will push in an electron, we will take, huh? No, they will repel. The electron will repel the incoming electron, and that is why they do not have much great electron affinity. However, chlorine has a greater electron affinity because it has empty orbitals. It has a bigger size. The electrons are not going to repel the incoming electron so much, and it can take away the electron easily. Okay. Alright. Now, nuclear charge. If the nuclear charge increases, electron affinity will also increase, of course. Right? More positive charge, more. The half-filled and the fully filled electronic configuration, they do not want to take in an electron. They will be like, I am already stable. Why should I mess my stability? I'm fine here. Don't bother me. Give it to someone else. Right? That's what they are going to do. Chal. Now everybody feels like I'm talking a little too much now. But yeah, I can't help it. I'm recording the session. I was taking a live session. If it was a live session, I could have spoken to you, but now I only have to make the jokes and I only have to laugh. What to do? Sad life of a teacher. Hashtag sad life you should start putting now. Anyway, in a period, the atomic size, it decreases with increase in the effective nuclear charge, and that's why we see there is an increase in the electron affinity as well. Okay. Although exception, mystery always there. What is the mystery here? The mystery is that the values of electron affinity of inert gases are zero. Why? At a fully filled stability they have complete stability. So why will they show electron affinity? They do not want to mess up their stability. They are like, Baba, I am absolutely fine. Do not mess with my stability. I am absolutely fine. You guys are searching for it. I already have it. I have that piece. Don't trouble me. That's why they do, and they do not want electron. Now, the values of electron affinity normally decreases when you're going from top to bottom in a group because the atomic size increases, which decreases the actual force of attraction by the nucleus. Are you getting my point? What are they saying? They're saying that value of electron affinity normally decreases as you go from top to bottom in a group. Why? Because the atomic size is increasing. If the size increases, the nucleus is not so close to the electron. The nucleus will not be able to pull in the electron. So the actual force of attraction by the nucleus is less. That is why. But exception is obviously there. Mystery is always there, right? The mystery is the values of electron affinity of alkali metals and for alkaline earth metals can be regarded as zero again because they do not have the tendency to form anions. They never want to accept electron. They're like, instead of me being in NS1 to NS2, I would rather give you that one electron and I will be the noble gas. That's better, more stability. Why should I have the fully filled stability when I can give away one electron and be noble gas? For example, most of you, everybody, you want to be an engineer, right? Why? Because you think that 4 years of struggle is much better than 8 to 9 years of struggle, right? Why do you want to do that? Similarly, these NS1 orbitals, these NS1 elements, they want to give away that one electron and they're like, bro, I can have the noble gas configuration. Same, you can be an engineer. That's your dream. You can be an engineer, you can make a great life out of it. Rather than choosing a 8 or 9 years of struggle where you're not studying, you don't know where to do, you have to start from a fresh level, entry level job, you would rather become an engineer and start directly from 10 to 15 lakhs of your salary. Won't you like that? That's exactly what they're doing. See, when you mix it with your story, you are understanding it, isn't it? Okay, guys, now we are going to have a look at electron affinity here, another exception. Now we all know that here, where do we have an exception? We have an exception. So we expect the electron affinity to increase as we go that side, isn't it? Yes. But we see that here there is an exception. Why? Neon is a noble gas. So the noble gas will not show you an electron affinity. It does not want it, right? Again, in case of nitrogen, you will be able to see an exception. Why? Because of half-filled p orbital. Okay. Then in case of beryllium, you will be able to see an exception. Why? Because of fully filled s orbital. Okay. You will be able to see fully filled s orbital, and hence they will also show you less electron affinity. So electron affinity of beryllium is less than boron, because boron still might want to catch an electron. Beryllium does not. Beryllium is like, I have fully filled, don't disturb me. Yes. So actual order of the electron affinity is fluorine has high, then it is oxygen, then it is carbon, then it is boron, then it is nitrogen, and then it is beryllium. Then it is beryllium. Okay. All right, everybody. Do we understand this? Now, electron affinity of the second period is lower than the electron affinity of the third period of the elements. Why so? Why so? Why so? Fluorine has, fluorine is supposedly, it is supposed to have a greater electron affinity. However, that's not the case, because like I told you, fluorine has a small size and the incoming electron experiences repulsion from the existing electrons. Hence, it does not want it. Okay. Similarly, here, see, chlorine, you would expect chlorine to have more electron affinity than sulfur, then phosphorus, and then silicon, right? But actually, what happens is silicon comes before phosphorus. Okay. Silicon comes before phosphorus. Okay. That is what is expected. That is what is expected. Chalo. That is what is the actual. Chalo. Here is a question, everybody. Let's try to solve it. Let's try to solve it. The electron gain enthalpy of chlorine is minus 349 kilojoule per mole. How much energy in kilojoule is released when 3.55 gram of chloride is converted completely into Cl minus ion in the gaseous state? Guys, let's solve it. Yes. Okay, what is given to you? Electron gain enthalpy of chlorine is given to you, which is 349 kilojoule. That means that 349 kilojoule energy is released, isn't it? Kilojoule energy is released. Is released when? Is released when 1 mole, when 1 mole of chlorine is converted, when 1 mole of chlorine is converted into Cl minus ion. Okay. Cl minus ion in the gaseous state. Okay. In the gaseous state. All right. Okay. We understand this. So then the energy released when how much? 3.55 gram chlorine we are converting. Okay. So the energy released when we are converting 3.55 gram of chlorine, where chlorine converted to Cl minus ion. Yes, how do we find that? We will find it as C. E is equal to 349 multiplied with number of moles of Cl. Okay. So that means 349 multiplied with number of moles. How do we calculate? Given mass by molar mass. Yes. So what is given mass? Given mass is 3.55 and molar mass of chlorine is 35.5, isn't it? 35.5 gram per mole. So if you calculate it here, 3.55, 35.55, you will have 34.9, isn't it? 34.9, and that means that option A is the correct answer. Check it out, guys. Check it out. Have a look and let me know. Is this the correct answer? Please have a look and let me know if this is what you are getting. Till then, I am going to drink some water. Alright guys, alright guys. Alright guys. Easy peasy biryani tasty. Yes, are we good to go? Let's move ahead. Chalo, let us move ahead. Next question. Okay, this is a JEE Mains 2020 question, everybody. That means quite recent, 2 or 3 years back. Which one of the following among each pairs will release maximum energy on gaining one electron? Who will release the maximum electron? We all know that in case of fluorine and chlorine, who will release more? Sorry, fluorine wouldn't want to accept the electron, isn't it? Fluorine won't want to accept the electron, so that's not happening, right? Because of the high electron repulsion. So the energy that will be released will be more by chlorine here. Okay, so chlorine will have more energy than fluorine. Then what about sulfur and selenium? Sulfur will definitely have more energy than selenium, right? Because it's on the top, so the electron affinity of the smaller electron is always higher. And then it is lithium and sodium. Again, no brainer here. Lithium will have more energy than sodium. So that means that it is option A that is the correct answer. I hope I'm not wrong. Please have a look, everybody. I guess it is option A, right? Yes. Chalo, cool. Moving on. Next question. Correct order of electron gain enthalpy kilojoule per mole of fluorine, chlorine, bromine and iodine is. Okay. Now we all know that fluorine will be lesser than chlorine. So it will be chlorine, then it will be fluorine, then I think it will be bromine, and then it will be iodine, right? Fluorine, chlorine, bromine, iodine, isn't it? So yes, it will be bromine, and then finally it will be iodine. Yes. So that means that I think it is option B. Please tell me, just because it kind of correlates with the data that we have. We know that chlorine is supposed to have a higher negative electron gain enthalpy. So it should be minus 349 because that's more. Fluorine will have lesser, and then it should be bromine, and then it should be iodine. Iodine is supposed to have the least. So I think it correlates. Please let me know if you are getting any other answer. Is this the answer that you all are getting? Yes. So can we again say that it is easy peasy biryani tasty? Yes, we can. Alright guys, now we have come to another trend, that is electronegativity. What is electronegativity, guys? Electronegativity is that, okay, this case is about bonded atoms. Now we are talking about bonded atoms. All this while, whatever we spoke about, it was not about bondedness. We were talking about one single atom. But right here, right now, we're talking about a bonded state. What happens is, here, for example, you have hydrogen and we have chlorine, right? Hydrogen and chlorine, they are bonded. Now, who is going to pull the shared pair of electron closer to it? That is called as electronegativity. Obviously, it is going to be chlorine. Chlorine is going to pull the atom closer to it. So, yes, chlorine is more electronegative. That means here, as the definition is saying, ability of an atom in a chemical compound to attract shared electrons to itself, and this is defined in a bonded state. To understand it a little better, I think I had look at this. Yes, this image right here. See how, let's say that hydrogen is also pulling, chlorine is also pulling, but chlorine is trying to pull it closer to itself, so this will become more electronegative. Are you getting my point? Yes, everybody? Great. Okay. Now coming back to it here, understand now, there was somebody called as Mulliken, and Mulliken scale gave the electronegativity as the average value of ionization potential and the electron affinity of an atom. What did Mulliken do? Mulliken said that electronegativity is actually the average of ionization potential and the electron affinity divided by 2. That's it. That's it. He said, okay, what is ionization potential? Ionization potential, ionization enthalpy, ionization energy, all the same. All the same. Okay, just write that. So this is called as your Mulliken scale. Okay, but that's not it. Now, one scientist has given one idea and that's it, or what? And then the science would not have, advanced at all. So after one scientist, now there is a second scientist whose name is Pauling. Pauling came up and he said that, no, I will tell you how to calculate it. And he said that the method for calculating the relative electronegativities of most element is given to you as delta is equal to xa minus xb is equal to 0.208, it's a constant, root over ea my ab EA minus B minus root over EAA multiplied with BB. For example, if you have the molecule HCl, consider H to be A and Cl to be B. Then the formula becomes here, everybody. The formula becomes delta is equal to XH minus XCl is equal to 0.208 multiplied with EH minus Cl minus, you will write here again root over EH multiplied with ECl. Getting my point? Yes. This is what is the formula. We will solve a problem. I think you will understand this better. And here it is written. EAB is equal to the bond enthalpy or the bond energy of the AB bond. EAA is the bond energy of the AA bond. Okay. AA means HH bond, CL bond. That is what they're talking about. Okay. Now, here what just happened, guys. Two of these things, they have they have merged into one thing. So I'm not able to understand. Wait a second. Let me just take out the slide here and my laptop so that I can see it. If whenever you download from Google Slide, no, these glitches, they always are seen. It's so annoying. Yeah, so it is. Okay, now here there is a scientist name called Alfred Roschow. Okay, he also gave something about electronegativity. So I am just cutting this down and I'm writing it here. Alfred Roschow. Alfred Roschow, electronegativity. Read this. I don't think in any other places you are able to read this, because I've seen the videos and I haven't found anything like this yet. But we have seen questions coming from Pauling scale, Mulliken scale. It's not very important according to JEE, but we have seen questions. Although it is very important for EM set. All the students who are studying for EM CET, yes, you do get questions from here. Okay. In JEE, I have seen that in 4 or 5 question paper, they have asked questions from this particular place. So that is why I'm teaching you. And what did he say? He said that electronegativity is actually the attractive force between the nucleus and the electron, which is at a distance equal to the covalent radius. So now we have electronegativity, which is equal to Z effective E square divided by R square, and that is equal to 0.359 multiplied with Z effective divided by R square plus 0.744. This is your Roshow's scale. Okay. Yes. So you have Mulliken, Pauling and Roschow, Alfred Roschow electronegativity. What is R? R here is the covalent radius of the atom. What is ZF? ZF is the effective nuclear charge. Do we make sense here? Okay. All right. Now what Pauling did was, Pauling did something interesting here. Okay. Listen to this. He assumed the electronegativity value of fluorine to be 4. And then what he did was, based on this, he calculated electronegativity values of all the other elements. Yeah, this was interesting. So as per Pauling scale, the elements, they have almost same electronegativity. Some elements like carbon and sulfur is equal to 2.5. Nitrogen and chlorine 3.0. Yes, P and hydrogen 2.1. CS and Fr is equal to 0.7. Beryllium, aluminium is equal to 1.5. So he did that. Okay. He did that. But what do we know? What do we know? We know that the factors that affect electronegativity is that as the size increases, electronegativity decreases. Right? Why? Because you are farther away from the nucleus. So it cannot happen. If the Z effective increases, electronegativity increases. Okay. All right, everybody. Yes. Now, let us talk about the charge on the cationic species here. So, if you have A3 plus A2 plus A plus 1, for the same element, you will see that A3 plus will have a greater the charge, greater is the electronegativity. Obviously, if it is 3 plus, that means that this particular ion has lost 3 electrons and it would want to gain the electron, right? It would want to gain the electron. So that is why it will have a more electronegative value, right? Now, in case of anionic, obviously it is opposite. in case of anionic, you see that A minus, yes, if it is just 1 minus, it will have a greater electronegativity than if it has 3 negative or 2 negative charge. Getting my point? Yes. Now hybridization. Hybridization I taught you, remember? Sp has the highest electronegativity. Why? Because in case of sp hybridization, you have 50% S character, 50% P character. And as you keep increasing for sp2, for sp3, what happens is that the length increases, yes, because P increases, the P character increases, S character reduces, and that is why electronegativity decreases. So we know that Sp will have a greater electronegativity than Sp2, and then it is Sp3. Guys, getting it? Everybody? Yes, I hope that you understand. Oh, final part. The final part here is moving from left to right along the period. You see that Z effective increases, electronegativity increases, and moving top to bottom down the group, size increases, electronegativity reduces. Okay. Now, why are we reading this? Acid, time pass. Why are we doing this? We're doing this because there are obviously applications. What are the applications? The metallic and the non-metallic character. Let's have a talk about this. The metallic character we have seen is inversely proportional to electronegativity. If the metallic character increases, electronegativity decreases. Yes, if the electronegativity increases, metallic character decreases. But the non-metallic character is directly proportional to electronegativity. Now, when the electronegativity of an element increases, we know that the metallic character decreases, which I have just told you, right? And it's the opposite. Now, when we talk about bond energy is directly proportional to electronegativity, guys. Yes, more is the bond energy, more will be the electronegativity. Okay. And when the electronegativity difference increases between two bonded atoms, the bond makes stronger and the bond energy of that bond also increases. Cool hai? We are about to finish the session, guys. We're about to finish this periodic properties lesson, and after that we have to read what? We have to read P block. Yes, we have to read P block. One second. Whew. All right. Yes. So as I was telling you, the applications are that bond length can be calculated. Yes. How do we calculate bond length? The bond length is inversely proportional to electronegativity. So we know that when the electronegativity increases between two bonded atoms, the bond length also decreases because of higher shifting of the bonded electron. Obviously, the bonded electrons will shift, isn't it? And that is why what happens is this size, the bond length decreases. Okay, the bond length decreases, right? Nature of the bond. Let's talk about it. The difference of electronegativity A minus electronegativity of B is equal to 0. That means that electronegativity of the A element is equal to the electronegativity of the B element. And the bond is purely covalent here. It's not going to be ionic. It's going to be purely covalent here. Now let us talk about the percentage ionic character may be calculated by using the Hensey and Smith equation. This is an equation. Please pay attention, everybody. How do you calculate? Percentage ionic character is equal to 16 multiplied with xa minus xb plus 3.5 multiplied with xa minus xb whole square. Here xa is the electronegativity of A and xb is the electronegativity of B. Got it? Clear? Alright. Then you can also calculate the acidic strength of the hydrides. Okay. In a particular period, acidic strength of the hydride, it depends on electronegativity of the metal in metal hydrogen bond. Okay, all of these things I think you can leave. I think you can study it as I will give you the notes. I have taught you this already many a times, but you get the trend, right? You also know that higher electronegativity of M means greater is the acidic strength of hydride. Okay. Now, nature of hydroxide. According to Gallies, there was another guy whose name was Gallies, and he said that in AOH, that is some hydroxide, yes, electronegativity A, if it is more than 1.7, then it will be acidic in nature. And if electronegativity of A is less than 1.7, then the AOH, the hydroxide, will be basic in nature. For example, you know that if the nature, imagine, okay? Consider an oxide. Let's consider AO. Yes. So if XA minus XO is greater than 2.3, we get a basic oxide. Okay. If XA minus XO is equal to 2.3, then you get amphoteric oxide. And if XA minus XO is less than 2.3, then you get an acidic oxide. Okay. All right, everybody. Yes. Now. Some more applications that is also there. You will get it. We already know these applications, I believe. I think that you already know it. Don't you know it? We also know that along a period, the acidic nature of the oxide increases. Yes, that we have studied in the P block elements. We have also studied in other places, in other chapter as well. But we know that along the period, the acidic nature of oxide increases. Why? Because you're shifting from metallic oxides to non-metallic oxides, and we know that non-metallic oxides are acidic in nature, metallic oxides are usually basic in nature. However, that's not correct. Plus 1 plus 3 plus 4 would be basic oxides of metals, but as the metal has more oxidation state, the acidic character increases, isn't it? Down the group, the basic nature of oxides increases. That also we know. For example, you know that for Na2O, MgO, for Al2O3, SiO2, you can calculate it and you can figure it out. Okay. All right, everybody. And I have also told you about amphoteric oxide in P block, which we will study in some time, right? Now, what is it? Hydrolysis product of AX. Here, A is some other element and X is your halogen. By chance, if the electronegativity of X is more than electronegativity of A, which is usually the case, right? Which is usually the case. We know that halogens have great electronegativity because they are short of one electron and they want to pull the electron bond towards them, right? Then on hydrolysis, the product will be HX. Okay. All right. But if the electronegativity of the halogen is lesser than the electronegativity of the other metal, then on hydrolysis you will get a hypohalous acid. Okay. For example, you will get Cl2O, where electronegativity of oxygen is greater than Cl. So on hydrolysis of Cl2O, you will get 2HOCl plus H2O. Okay. Now, nomenclature of inorganic compounds, this you don't have to read it, forget about it. Chalo. Now let us solve a question here. The question is, everybody, calculate the electronegativity of carbon from the following data. Yes. So you are given EHH is equal to 104.2 kilocalorie per mole. ECC is equal to 83.1 kilocalorie per mole. ECH is equal to 98.8 kilocalorie per mole. XH is equal to 2.1. So we have to calculate. How do we calculate? We know the formula. What is the formula, everybody? What is the formula? The formula, everyone, is for XC minus XH, right? For XC minus XH, okay, I'll move this side. What was the formula? You write a constant, that is 0.208, okay? And then what do you do here? You write here ECH, EC minus H minus ECC multiplied with EHH. Am I right? Yes, this is it. This is it. So now what do you have? You have XC minus XH value is given in the question 2.1. So write 2.1 is equal to 0.208. Now ECH is given to you 98.8. See, 98.8. So write down here 98.8 minus ECC is given to you, that is 83.1 multiplied with EHH is given to you, which is 104.2. All right. Calculating this all over, everybody, do calculate it and let me know what is the value of XC. Yes, do let me know in the comment section what is the value of XC. You just have to calculate it. I have left it all. I have substituted the values in the formula. All you have to do is just calculate it. You just have to find one single number, find it out and tell me the answer in the chat box. All right. Yes, so moving on to the next question, everybody. This is a JEE Mains 2019 question, everybody. And the question is, in general, the properties that decreases and increase down a group in the periodic table respectively are. Which one increases down the group? increases down the group is atomic radius, right? And what is it that decreases down the group? If atomic radii increases, ionization enthalpy decreases, right? We know that ionization enthalpy decreases. If ionization enthalpy decreases, that means that electronegativity will decrease. Electronegativity will decrease, right, as we go down the group. And we know that atomic radius increases down the group. So that means option C, electronegativity and atomic radius. Please let me know, is this the answer that you all are getting? Yeah, is this the answer that we all are getting? We are. Very good. Great. Okay. Next question. The correct option with respect to Pauling's electronegativity values of the element is it tellurium greater than selenium? Is it gallium lesser than germanium? Gallium should be lesser than germanium, no? Silicon lesser than aluminium? Or is it phosphorus greater than sulfur? What do you think, guys? We know that electronegativity increases across a period because of the number of charges of the nucleus, right? Effective nuclear charge. That means that it will attract more bonding pair of electrodes. Yes. So you have Bal Gangadhar Indian Tilak chemistry sir gives. So germanium is in the next period. Germanium is in the right side of the period. So I think yes, option B is the correct answer. I think it should be the correct answer because electronegativity increases across a period. So yes, for germanium it should be more. Right. Okay. All right. Oh, and finally we have come to the diagonal relationship, which we know very well that there are certain elements which exhibit this property of diagonal relationship, especially in case of lithium, magnesium, beryllium, aluminium, boron with silicon. You get to see a relationship, yes? And on descending a group, the atoms and the ions, they increase in sizes. On moving from left to right in the period, the size decreases, and thus on moving diagonally the size almost remains the same, which is why they show you a similar property, and that because it is diagonal, we call it to be a diagonal relationship. That's it. Easy peasy, right? Easy peasy. Now for example, lithium has a size of 1.23 angstrom. Magnesium has 1.36 angstrom. Not too much difference. Lithium, it is 0.76 angstrom, Li plus, lithium plus, and Mg2 plus has 0.72 angstrom. See, once again, not so much difference, okay? Alright, the diagonal relationship you also get to see in case of electronegativity values. Yes, lithium has electronegativity value 1, magnesium has 1.2, beryllium has 1.5, aluminium has 1.5, boron has 2, silicon has 1.8. That's it. The charge to ionic ratio, radius ratio is also nearly similar here. For beryllium, it is 0.45 angstrom, and for aluminium 3 plus, it is 0.535 angstrom. But the charge ionic radius ratio is very similar because the charges are also 2 plus and 3 plus, right? Okay. Now here is the question, everybody. Let's solve it. This has come in JEE Mains 2019. Believe it or not, the electronegativity of aluminium is similar to beryllium, isn't it? You did not even have to think. You did not even have to pick your pen. So yes, JEE Mains does ask you such similar questions as well, and you know the answer. And guys, with this note, we are done with periodic properties. This is the question they will be asking you from periodic properties. These are the trends. These are the exceptions that they will ask you. So please follow it properly. And now we are going to start with P block elements. Let's go. Chalo. All right. So then now we are going to complete P block 13 to 18. We have started with periodic properties and now we are moving completely towards P block, everybody. Okay, so here we are, and I hope that you all know where P block is. I do not have to tell you about all of that. P block is right here. Which side? wait, let me check. This side. This is P block, yes. From boron family to your noble gases, they are all included in the P block, and we all know that the general electronic configuration of the P block from group 13 to 18 is NS2, NP126, everybody. Right? Now for group 13, everyone, you know what, let me write it down here, okay? For group 13, what is For group 13, what is the electronic configuration? The general electronic configuration is Ns2np1. And remind you everybody, this P block lecture right now, right here that I'm taking, it is according to, as per the revised syllabus. This is where we are going to get the questions from. So please study it and make sure that you are focused here, okay? Group 14 has an electronic configuration, general electronic configuration of Ns2np2. Group 15 has a general electronic configuration of Ns2np3. Group 16 has Ns2np4. Group 17 has Ns2np5, and by now I'm sure that you all know Group 18 obviously has Ns2np6. Yes, completely filled stability. That's what we see. All right. Yes. Now, my dear students, what are we going to do? We are going to take a look at each and every group, right? Now, we know that when we are moving from left to right, the more number of oxidation state is possible, as we can see that there are Ns2np5, isn't it? So, there is a possibility of more oxidation state. And in this block, we do get metals, metalloids and non-metals that we have already spoken about in the periodic properties as well. Which are the ones that are metalloids? Goths are silly aunties, that is germanium, arsenic, selenium, antimony and tellurium. These are your metalloids, okay? These are your metalloids. All right, everybody? Yes, yes, yes. Makes sense? Nonsense? Great. Now we are going to come across group 13. The group 13 elements, that is your boron family. Your boron family looks like Bal Gangadhar, Indian Tilak. And the last one is neonium. Okay, last one is neonium. All right. And here is the electronic configuration that is written. Once again, like I told you, just to save on some time, everything is written here. I'm not writing it down. But if you want to watch a session wherein ma'am has written the notes, then that is also available. But I had recorded it some time back, just after NTA had disclosed the revised syllabus. That's when I have taken it. It's there in the channel. You can just look for it and you will find it. Okay. All right, everybody. So here, what do you have? You have boron family, boron, that is 2s2 2p1, and you know, whenever you are writing down the electronic configuration, always write down here the noble gas. That's how you write it down. For neon, it is 3s2 3p1. For gallium, it is argon 3d10 4s2 4p1. And do remind you, let me tell you everybody, here is the introduction of the d orbitals that we have already spoken about in the periodic properties as well. Okay, and then you can see for indium it is 4d10 5s2 and 5p1. For thallium it is xenon 4f14 5d10 6s2 6p1, and for neonium it is radon 5f14 6d10 7s2 and 7p1. This is the general electronic configuration. Now, let us have a look at the atomic radius, ionization energies and electronegativity, which we have just observed it some time back, but it is my duty to teach you right now. The general oxidation state, okay, the group oxidation state, that one oxidation state that all of these elements can exhibit, my dear students, is your +3 oxidation state. How so? NP1, they can remove one electron, sorry, and they can also remove 2 electrons from right here. So +3 is the general oxidation state. What about the atomic radius? The atomic radius, which we have just spoken about, we all know it is first boron, then it is aluminium, but aluminium is slightly greater than gallium, and then it is indium, and indium and thallium, they have almost equivalent atomic radius because of the poor shielding effect of f orbitals, and that has been introduced just before indium, right? Okay, getting it? Gallium also has extensively low melting point, and it can exist in liquid state during summer in your palm, everybody. Why so? But it also has very high boiling point. That is why it is used as a it is useful for measuring high temperature. Whenever you want to measure high temperatures, you can use gallium as a thermometric liquid because it has very high boiling point, but it has low melting point. All right, everybody. Yes, is this clear, guys? Is this clear? Now, atomic radius, I have told you already. Ionization energy order, but choose ionization energies as well. We can see that boron has the highest ionization enthalpy. Then you have thallium, then you have gallium, then you have aluminium, and then you have indium. Why is there a sudden twist in case of thallium and gallium? That's because we know that in case of thallium, f orbitals has been introduced just before thallium, and for gallium, d orbitals or d elements have been introduced, isn't it? Yes, we know this, right? Then when we come to electronegativity order, we once again know that in case of electronegativity as well, boron has the highest electronegativity because of its smaller size. But we see that thallium comes in the next order. Why? Because thallium, once again, because of the f orbitals introduction, it has such worst shielding effect that the atomic size reduces, and that is why we see that the electronegativity is also slightly increased here. Okay, then it is indium, then it is gallium, and then it is aluminium. All right, that is the case about your electronegativity. Clear hai everybody? Is this clear, guys? Yes, sorted here, sorted. Yeah or no? Yes or no? Yes or no? Okay, now we know that generally, yes, when we talk about ionization enthalpy, we know that top to bottom it is supposed to decrease. However, that does not happen just because of the poor shielding effect of f orbital and d orbitals which were introduced here. Okay, electronegativity, we have spoken about it, yes, and we know that what is electronegativity? It is the attraction of the bonded electron, and attraction of the bonded electron, or we can say that the attraction of the shared pair of electron, and boron has the highest. All right, boron has the highest. Okay, now we are going to talk a little bit about the oxidation state. And oxidation state, like I told you, the group oxidation state, that is the most common oxidation state of all the elements that are present in this boron family. It is +3. Everybody, can you see? Boron, aluminium, gallium, indium, thallium, all of them show you +3 oxidation state. However, gallium, indium and thallium, they can also show you a +1 oxidation state. Why +1 oxidation state? That's because as you go down the group, we notice something that is very weird. And what is this weird thing? It's called as inert pair effect. What is inert pair effect? What is inert? Inert means that somebody is not going to mingle, right? Pair means two electrons, right? Who has two electrons? Is the s orbital that has two electrons. So inert pair effect, that means the s orbitals that we have. Remember the group oxidation state. What is the group oxidation? No, not group oxidation. The group electronic configuration, ns2 np1. That means that this ns2 electrons, they are going to act like they are inert. They are not going to participate in the reactions, which is why you suddenly start seeing the +1 oxidation state more in the picture. Now, why is this +1 oxidation state becoming more dominant or more prevalent as you go down the group? That's because the d and the f orbitals have been introduced, and they are very poor shielders, right? Yes, they have absolutely poor shielding effect. So when they are introduced, because of the d and f orbital, now the nucleus can look at the electrons and they are trying to pull the s orbital. The s orbitals now are bonded to the nucleus. They are not going to act like they can participate. Hence, only p orbital electron, that is np1, is available for the bonding. And that, my dear student, is your inert pair effect. Are you getting my point? Yes. So the p block element, they show this higher oxidation state, and they also can show you the lower oxidation state, and this is absolutely attributed to the inert pair effect. Now you will find that as you move into any other group, you move to group 14, group 15, group 16, group 17, you will see that the bottom elements, they start showing a lower oxidation state, and only because of this inert pair effect. This is the most prevalent, and this is the main reason why they show you this, why they show you these lower oxidation state. Okay, now we are going to talk a little bit about the physical properties, and we know that here we are going to talk about the melting point, the boiling point, and the density, everybody. Now, if you look at the melting point, you see that boron has a really high melting point. Yes, you know why? Because boron also has a very strong crystalline lattice, so much so that it is almost resembling diamond. Yes, boron has a very strong crystalline lattice, and it is almost like diamond. It has really high melting point, as you all can see, really high boiling point. Comparing to all the, in comparison with all the other elements that are present in this family, you can see that boron has the highest melting and the boiling point. Okay, All right, only because of this very strong crystalline lattice that they have. Boron is non-metallic, it is extremely hard, it is black colored, and you can see that gallium in the same family has extremely low melting point but really high boiling point. These are all. Now, when you talk about aluminium, gallium, indium, and thallium, they are soft metals and they have lower melting point and high electrical conductivity. And we know that the best metals that we have, they are in the D block because of variable oxidation state. They have better bonding, right? Like manganese or iron. Why are they so rigid? That's because of more electrons available in the kernel for bonding, right? Right, everybody? Getting my point? Exactly. Great. Okay, so we are done. Now let us try to solve a question here, and the question, everybody, is consider the following standard electrode potential in aqueous solution. For elements M3 plus 2M is aluminium is minus 1.66, M plus M is plus 0.55, thallium is 1.26 and minus 0.34. Based on this data, which of the following statement is correct? TL plus is more stable than Al3 plus. Yeah, that is true. That is absolutely true. Right. That is absolutely true. Al plus is more stable than Al3 plus. No, not at all. Tl plus is more stable than Al plus. Is that right? Is that right? TL plus is definitely more stable than Al plus. Yes, that is true. TL plus is more stable than Al3 plus. No. That's not wrong. That's not true. Sorry. TL3 plus is more stable than Al3 plus. Not at all. Absolutely wrong. So I believe that the correct answer is TL plus is more stable than Al plus. Option C makes sense because we just saw that thallium will show +1 oxidation state and that will be more stable than aluminium plus because of the inert pair effect, right? Yes, so option C is the correct answer. Now guys, moving ahead, let us go to the group 14. Group 14 has obviously the best of the best because of whom we learn the whole organic chemistry. Yes, and who do you have here? You have chemistry sir gives snappy problems, and here also you can see that the group electronic configuration is ns2np2, everybody. Yes, and which is why you see that carbon has 4 electrons that it can form bonds with, which is why it shows catenation. But catenation is no longer in your syllabus, everybody. You only have allotropes of carbon, that's it. Okay. Yes, and we see that as you move down the group, the metallic character increases in this group. The metallic character increases, as you all can notice, everybody. Yes, you see that carbon is the non-metal, silicon is the non-metal, then you have germanium, which is a metalloid. And after that, you have tin and lead, which are both metals. Okay, these are both your metals, everybody. All right, guys. Yes, making sense or nonsense? I hope that you all are getting it right. Yes. I hope that you all are getting it right. Now, as you go down the group, you also see that the size increases and the covalent radius. What happens to the covalent radius? The size increases. That's what I said, right? Because why? The atomic radius is also increasing, isn't it? So if the atomic radius increases, then obviously the covalent radius is also increasing. Why? Because down the group, the size increases. Correct. That's it. Okay. Now, what will happen here? What will happen here? What do you think, guys? What will we see? We will also, once again, we will see here that even in this case, that as you go down the group, guys, what will you see? As you go down the group, what will you see? Any idea? Any idea what will happen to the oxidation state? Exactly, very similar to what has happened in the 13th group. We will notice that here as well. Okay, so chalo, let us talk about the atomic radius without much further ado. What will we see? Atomic radius here will be carbon will have the lowest, then it will be silicon, then it will be germanium, then it will be tin, and then finally it will be lead. Here there is not much of an exception here. Okay, there you will not see much of an exception here. Why did we see it in group 13? Because just before group 13 you had the whole lot of D block elements, right? But in this case somebody else is taking the brunt of it already, so we will not see much of an much of an exception here. Okay, then we come to ionization energy. Now, ionization energy, we see that carbon has the highest, then it is silicon, then it is germanium, and then there is a switch. There is a switch. In case of lead and tin, you see a switch. You see that lead comes before tin. In this case, once again, because of the f orbital introduction, we see this, okay? And in case of electronegativity, we see that tin, germanium, silicon are almost similar, but lead and then carbon right here will have the highest electronegativity once again. Why? Because carbon is of the smallest size. And we will be talking about the anomalous properties of the first atom of the group right now, right here. We all know that because they are the smallest in the family, they behave a little weird, right? They have their own tendencies, own desires, and they will do that, okay? So all these elements, they belong to the second period. You see, boron, carbon, nitrogen, oxygen, fluorine, all of them, they belong to the second period, and they have only ns and np orbitals. They do not have the d orbital, which is why they can never show you any hybridization such as sp3d2, sd2sp3, sp3d. They cannot show you these kind of hybridization. They can only show you sp2, sp3 hybridization, because that's the only orbital that they have, right? Yes, so because of this absence of d orbitals, they cannot even expand their covalency. Their highest covalency is only whatever they have. For carbon, the highest covalency is 4, but that's not the case with, as you go down the group, you see that their covalency increases. They have flexible covalency. Why? Because they have d orbitals which are empty. Yep, the d orbitals are empty. That is why, okay? That is why. All right, everybody. Yes, guys. Is this clear? Oh, by the way, I also forgot one thing to mention, that is boron also has something called as icosahedron structure. Please do remember it. Boron has an icosahedron structure which has 20 faces and 12 corner points, and that is why it has a crystalline solid, strong crystalline solid lattice. And what does it do? It is very, very, very high melting point. Okay. All right, everybody. Yes, guys. Chalo. Moving on, moving on, moving on. Now, oxidation state, everybody. See, I told you, similar oxidation state. You will be able to see it here. Now you see, carbon shows you +4 oxidation state, silicon shows you +4 oxidation state, but the moment you start going to germanium, you see a +4 and +2 oxidation state, tin +4 and +2 oxidation state, lead +4 and +2 oxidation state, and as you go down the group, the lower oxidation state becomes more dominant, more prevalent. Why so? Inert pair effect. Yes, inert pair effect. The lower oxidation state is always attributed to inert pair effect. That's what you are going to write, okay? All right. Yes, guys. Moving on. We see that all the group 14 elements, by the way, are solids. Yes, they do show catenation, but only carbon and silicon can show catenation. Lead cannot show you catenation at all. Lead cannot show you catenation at all. All right, everybody. Yes, guys. Is this clear? Is this clear? Yes. Okay. Cool, 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 cool. All right. Okay. Now, guys, we are moving on. We are moving on, and we are going to understand. We are going to understand what? 1 second, guys. 1 second. 1 second. I'm going to tell you. 1 second. Yeah, there are a few more things that we have to talk about. Few more things that we have to talk about. Occurrence, I don't think it's there anymore, right? Occurrence is not there. Occurrence is not there. Yeah. Occurrence, we don't have to talk about it. Yeah. Okay. Yes. Melting point, everybody. Melting point. If you take carbon, okay. If you take if you take carbon as in bole to graphite. Huh. Before melting point, let me tell you about density, everybody. Yes, density is something that I want to tell you about. If we talk about the group 14's density, and if we take, let's say, graphite, okay, carbon graphite, if we take, then what happens is this will be lesser than your silicon, then it will be germanium, and then it will be tin, and then it will be lead, okay. But by chance, if you want to take a diamond for carbon's allotrope, then what will happen is you will have silicon here, then it will be lower than carbon's diamond, okay. Then you will have, as usual, whatever I have just told you, okay. In case of melting point, we see that it is carbon, then silicon, then germanium, then tin, and then lead, okay. But there is a slight difference here. If you notice, everybody, lead has more melting point than tin. Why so? Because of lanthanide contraction, okay. Because of lanthanide contraction, we see that there is a switch here, okay. There is a switch here. All right. Now, in case of boiling point, we see that it is usual. In case of boiling point, you are not going to be able to boil carbon, everybody, yes, but you can boil silicon, germanium, tin and lead. That is as simple as it is. There are no exceptions here, okay? All right, everybody. Apart from that, oxidation state, I have already told you, right? Oxidation state, I've told you. And I have told you about the stability. Now, you will see that the lead in +4 oxidation state will have the least stability. However, lead in +2 state will have the highest stability. Yes, and lead Pb +4, okay, Pb +4 is going to be a very good oxidizing agent because it will directly, it will try to reduce to Pb +2. What did I say, everyone? What did I say? I said that Pb +4, yes, Pb +4 would want to reduce to Pb +2. Hence, it is going to be a good oxidizing agent, everybody, because we know that Pb +2 is more stable than Pb +4, right? And similarly, when we are talking about Sn, yes, when we are talking about Sn, we notice that Sn +4 is more stable, okay? What do we notice? We notice that Sn +4 is more stable. Why so? Sn +2 is not very stable and hence it oxidizes to Sn +4. That means that this is a good reducing agent. Okay, this is a good reducing agent. These kind of questions they may ask you and they may merge it with redox chapter and they can ask you about this. Okay. All right, everybody. Is this clear, guys? Is this clear? All right. Now, shall we try and solve a question? Let us try and solve a question here. GE2 compounds are powerful reducing agents, whereas PB4 compounds are strong oxidants. It can be due to PB is more electropositive than germanium. Ionization potential of lead is less than that of germanium. Ionic radii of Pb +2 and Pb +4 are larger than those of Ge +2 and Ge +4. Or is it because of the more pronounced inert effect in lead than in germanium? I think that option D makes more sense to us, isn't it? Option D is the correct answer because it has more pronounced inert pair effect than in lead. In lead than in germanium. So yes, option 4 is our correct answer. See, we solved it. We solved it. Now, next question, guys. The stability of tetrahalides of silicon, germanium, tin and lead increases in the order. Tetrahalides, okay? Tetrahalides, we are not going to even talk about the halides part here, but we know that Pb +4 will have the least stability, then Sn +4, then germanium and then silicon +4. So I think option A is the one that is making sense. Yes, absolutely. You don't even have to see what is with it, but you know that the oxidation state of the lower elements, that is the bottom elements in P block, they will always prefer the lower oxidation state because of inert pair effect, right? Now we are going to talk a little bit about the allotropes of carbon, everybody. Yes, we are going to talk about the allotropes of carbon. So everybody ready? Shall we do it? No? Yes? What do you think? What are we guys doing? Everybody, I hope that you are still writing the notes and you are not thinking that, oh, ma'am will give us everything, so it's fine. Yeah? No, don't do that. Yeah, don't do that. Shall we? Yeah? Let's do it. Shall. Now, allotropes of carbon, we also know before allotropes, we also see that catenation. Carbon atom, they have a tendency to link with one another through covalent bonds and they form chains and ring, which is called as catenation. Now, order of catenation means we know that carbon can show you much higher catenation than silicon and then germanium, and tin and lead does not even show catenation. Lead too does not show catenation at all. Now we are coming to the allotrope part. In case of diamond, everybody, diamond is an allotrope of carbon and here hybridization is sp3. The carbon carbon bond length in diamond is 154 picometer. The C double bond C bond length, it is not available in diamond. Okay, in diamond you do not have C double bond C. But what is the delta HF, kilojoule per mole? That is 1.9, and density of diamond, as you all can see, it is much higher. It is 3.51. Now we come to graphite. In graphite, the hybridization is sp2. In the CC bond length, everybody, is 141.5 picometer. And similarly for fullerenes, Buckminster fullerene, the one that looks like a football. Yes, exactly. Here also you have sp2 hybridization and the CC bond length is much similar to the graphite. This is 143.5 picometer, whereas in case of graphite it is 141.5 picometer. The C double bond, C bond length are also much similar here. If this is for graphite, it is 141.5 picometer. Then for fullerene, it is 138.3 picometer. Delta HF, see graphite, you are, for graphite, you are going to get it as 0, and for fullerenes, it is 38.1. Okay. Density for graphite, it is 2.22, and for fullerene, it is 1.65. That's it, that we have to study almost. But right here, I also have a table which you can go through and you can learn it at your own pace. I don't think much is going to be asked, but please understand certain of the things that might come here. Okay, first of all, that diamond is one of the hardest next to boron nitride. That's something that you have to remember. Each carbon atom is linked to 4 other carbon atom in tetrahedral manner. Yes, tetrahedral manner. Alright, uses, forget about it. Now we come to graphite. Graphite has layered structure. Layers are held by van der Waals forces, right? The electrons are delocalized over the whole sheet and they conduct electricity along with the sheet, that you know. They're good conductor, but forget about it, you already know. Thermodynamically most stable form of carbon. Now do you understand why it is 0? Because thermodynamically it is the most stable compound or most stable allotrope of carbon. Okay. Alright, it is very soft and slippery, so it is used as a dry lubricant in machines. Alright, moving on here. Now we come to fullerenes, everybody. Fullerenes, you know, heating graphite in an electric arc in presence of inert gases such as helium or argon can result into a fullerene. You will get a cage-like molecule here. This is called a C60 soccer ball shaped Buckminster fullerene. You know about this. There are 26 membered rings and 12 5-membered rings. This is important. Please do read it. Okay, this is important. Read it. The 6-membered ring is fused with 6 or 5-membered ring. All right, here you get it. And then the 5-membered ring is always fused with a 6-membered ring. Remember this. So these 3 points about fullerene is important. Okay, these 3 points about fullerenes are very, very, very important. All right, guys. Chalo, moving on. So these are the few things that you have to remember about the allotropes. If I remember something, I will let you know, but this is what is written. If there is anything extra, I will let you know in the session. Don't worry about it, okay? Now let's quickly go to the group 15 elements, everybody. In group 15 elements, what do you have? You have the nitrogen family, where you have nitrogen, phosphorus, arsenic, antimony, bismuth, and moscovium. Moscovium is the last element, which is once again a radioactive element, everybody. Okay, what is it? It is a radioactive element. That means that the topmost elements, that is nitrogen and phosphorus, these are non-metals. Yes, arsenic and antimony are metalloids, and bismuth, moscovium, both are metals. However, bismuth is a metal and moscovium is a synthetic radioactive metal that we have created. Not me, but yeah, human beings we have created. Okay. Now here, what is the electronic configuration? The electronic configuration is Ns2Np3, and we have spoken about it in periodic properties that because of this Np3, the half-filled stability, we see a much more stability than all the other elements in the P block. Right, we see that there is a switch in the ionization enthalpy, there is a switch in the electronegativity, right? All of these we have seen in the periodic property, so I don't think there is a point in repeating it. Do we need to? No, we don't. Now in this case, you see that the common oxidation state for the whole group is obviously 3. That is the common oxidation state. Common oxidation is 3. Now what happens is, because of electronegativity and small size, did you know that they can also show you +3 oxidation state? They can lose all the Np3 electrons and they can show you +3. They can also show you -3. -3 is the common oxidation state. Because of small electronegativity and small size, they can gain 3 electron or they can lose all the 3 electron. And guys, because of Ns2Np3, you see that there are 5 electrons right here. So yes, they can also show you +5 oxidation state. Okay. All right. Now, obviously, as you go down the group, the tendency to show this -3 oxidation state, that decreases. Why so? The size increases. If the size increases, then the electronegativity is also going to decrease, right? And that is why the tendency to show -3 decreases. Now, because of the inert pair effect, the stability of +3 oxidation state increases and the stability of +5 oxidation state decreases. All right. Yes, as usual, whatever we have seen in the past groups as well. Okay. Now, let us talk about quickly the atomic and the ionic radii, and we see that increases down the group, obviously. What is the reason? Because you are increasing the number of inner shells as well. So, obviously, the atomic and the ionic radii will increase, right? Ionization enthalpy. What happens to ionization enthalpy? That decreases down the group. What is the reason? The reason is that there is an increase in atomic size. Then we have electronegativity, which decreases down the group, and yes, the reason is that there is increase in atomic size. All right, everybody, are we clear with this? Are we clear with this? Great. Okay. All right. Yeah. Huh. Now guys, we are going to talk a little bit about the thermal stability. The thermal stability of the hydrides, okay? Thermal stability of the hydrides. But before that, I also want to tell you about, one second. Let me find a empty space. I want an empty space. Do I not have any empty space? Okay. Can I write it here? I think I'll write it here, okay? All right, let me tell you about the different oxidation state in nitrogen and phosphorus, and please listen to me very carefully. Now, nitrogen can show you -3 oxidation state. Yes, it can show you +1 oxidation state. It can show you +2 oxidation state, +3 oxidation state, +4 oxidation state, and +5 oxidation state. Now, this +1, +2, and +4, when it reacts with oxygen only, this +1, all right, +1, +2, and the +4 oxidation state is shown by nitrogen only when it reacts with oxygen, not in other cases, okay? All right, now let us talk about phosphorus. Phosphorus can show you -3. Why am I writing +3? No idea. Phosphorus can show you -3, it can show you +1, it can show you +3, it can show you +4, and it can show you +5. So the only oxidation state that phosphorus cannot show you is +2 oxidation state. However, it shows +1 oxidation state and the +4 oxidation state only in case of oxo acids, not otherwise. Okay, not otherwise. Nitrogen can show you +1 to +5 oxidation state when it disproportionates. There are a lot of disproportionation reactions related to nitrogen compound, and you will see that from +1 to +5 oxidation state is visible in those reactions. Okay. All right, everybody. Phosphorus in its intermediate oxidation state also disproportionates into +5 and -3. For those that also there are reactions, and I am also going to show you a little bit of the oxidation states, because I'm not going to teach you, but I'll give you a list of the oxidation state, because I think I have a hunch. I feel like that they may ask you, they will just pick up any oxo acid and they will ask you to write down the oxidation state, because that is related to redox reaction. I just think that that might happen. They are telling you that no, 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 it will not come, it will not come. But I just have a hunch that they might just ask you like one sort of question like this. And that is why I'm going to give you the list. You can follow it, okay? All right, yes. Covalency of nitrogen, as you all know, that because it has only S and P orbital, that means that nitrogen's covalency is only 4 orbital, 4 bonds. That's it. It cannot maximize its covalency because there is absence of d orbital. However, phosphorus, arsenic arsenic, antimony, bismuth, they all have d orbitals and they can expand their octet, which is why you will see that pF6 exists. But have you ever noticed that NF6 exists? No, no, no. It doesn't, right? It doesn't. So what do we say with this weird behavior of nitrogen? This is called as anomalous behavior of nitrogen. And why does it show? It shows this anomalous behavior because of small size, high electronegativity, high ionization enthalpy, absence of d orbital. Nitrogen can form multiple p-pi bonds with itself, or of atoms that are of similar size, like nitrogen and oxygen, nitrogen and carbon. It can do that, right? But have you seen phosphorus forming a lot of p-pi bond? No, it doesn't. The other elements, they can also form p-pi d-pi bonds or d-pi d-pi multiple bond. Now what is this p-pi d-pi d-pi? How do you calculate it? All of that I've taught you in chemical bonding. Go and watch it. Go and watch it. Okay. Now guys, we are going to take a look at the chemical reaction, that is reaction with hydrogen. When this nitrogen family, they react with hydrogen, what do they form? They form hydride of the nature this EH3, okay, of the nature EH3. E bole to element. Let us consider E as the element and then H3. Why H3? We have just spoken about the common oxidation state and everything, right? So obviously it will form EH3. Now what happens is that here you can get to see the thermal stability. NH3 has the highest thermal stability, then PH3, then ASH3, then SBH3 and then BiH3. But if we want to talk about the acidic strength, what do you think will be the acidic strength, my dear students? The acidic strength will be as simple as the reducing characteristics, because we know whoever has a larger size will be able to get rid of the hydrogen atom and hence acidic strength increases, isn't it? Great, absolutely right. So reducing nature, acidic strength, same, okay? Then we come across basicity. Basicity will be exactly opposite of the reducing characteristics or the acidic strength that I have just spoken to you about, okay? Now guys, the melting point and the boiling point is a little important here, okay? The melting point and the boiling point is slightly important here. Have a look. You have pH3, ASH3, NH3, SBH3 and BiH3. This is your boiling point. Now melting point, I'm writing it down here. Everybody please have a look. You see that melting point here is NH3, then it is BiH3, then it is SBH3, then it is ASH3 and finally it is PH3. PH3 has the least melting point. Why so? Because we notice that the reason about boiling point, for boiling point the reason is that there is an increase in size, and NH3 in exception is because of hydrogen bonding. In case of NH3 you get to see hydrogen bonding, which is why it has increased, okay? Which is why it has increased, everybody. So this is slightly important. All right, yes, basic character I have already told you. I think that's it, okay? Now guys, here are certain questions and the solution is also written here, and these questions are very important for your board exam. But choose your board exam, this is very important. So whenever you want to also prepare for your board exam, see, one session is going to help you prepare your board exam as well as JEE. These questions I am not going to teach you right now, but I am going to give you the PDF in which you can go through this. Why am I giving you the PDF? Number one, these are slightly exceptional questions, right? These are questions that are related to the exceptions of the P block elements. So they may ask you exceptions related questions in JEE. So just go through it, okay? And they may ask you subjective questions in your board exam. So just please go through them. These are important questions. Like for example, nitrogen exists as a diatomic molecule, that is N2, while phosphorus exists as a tetraatomic molecule, P4. Why? The answer is the fact that because phosphorus cannot form multiple pi bond. I told you. Yes, this strength, this power is only with nitrogen. Only nitrogen can form multiple pi multiple bond, and not only with nitrogen, but it can also form pi multiple bonds with other atoms which are of similar size, like carbon or oxygen, right? Okay, got it? Clear? Yes. Now, similarly, you have other questions here. These are the 2-3 slides that are filled with these kind of questions. And now we are going to solve this question, which is, which of the following statement is wrong? Which of the following statement is wrong? The stability of hydrides increases from NH3 to BiH3 in group 15 of the periodic table. That is true. Nitrogen can't form d pi p pi bond. That is true. Single NN bond is weaker than the single PP bond. Is that true? Is that true? That is true. N2O4 has two resonance structures. What do you think, guys? Which one is right? Which one is right? Come on, guys, think about it. Let me give you some time here. Let's see if you can solve it. Let's see if you can solve it. Come on, guys. Come on. Quickly, think. I want you all to think, guys. I want you all to think. The stability of hydrides increases from NH3 to BiH3 in group 15 of the periodic table. Nitrogen can't form p pi d pi bond. That is true. Yes. Single NN bond is weaker than the single pp bond. That is also true. You know why? Because when you have a single NN bond, nitrogen has a lone pair, right? Nitrogen also has a lone pair. These lone pairs, they repel each other. Because of the smaller size of nitrogen, the lone pairs, they will repel each other, and hence the P single bond is actually much stronger. That is true. This is true. N2O4 has two resonance structure. This is also true, actually, yes. But the stability of hydrides increases from NH3 to BiH3. No, but just have a look. Yes, I just told you that it is true only because I wanted to confuse you. Have a look. No, NH3 has the highest stability, guys. BiH3 is in fact less. So it decreases. That would have been the correct answer. So this is our correct answer. This is the one that is wrong. Option A is the correct answer. Okay. Alright guys, moving on, anomalous behavior of nitrogen. I think I have just explained it to you that what is the anomalous behavior, right? But here are certain bit of more things that you can read from here. Nitrogen has absence of d orbital, and that is why the covalency is only restricted to 4. Nitrogen cannot form d pi, p pi bonds in the as the heavier elements can. And what else here? Nitrogen has unique ability to form multiple p pi bonds. I've told you nitrogen have poor catenation tendency. I've told you about these also, right? Now here guys, this is what I was telling you. These are the oxides of nitrogen. These are the oxides of nitrogen. I do not think that this is included in your portion. I do not think that this is included. Yes, but I will suggest that please go through the formula, the name, and the oxidation state of nitrogen that is corresponding to the compound. Why? Because there is a chance that they may merge this question with a redox chapter, and they may ask you about the oxidation state. There are these many oxides, yes, these many oxides, but I'll give you a little bit of brief here, okay? I'll give you a little brief about the oxidation and how they react with oxygen, right? So when nitrogen or this family, they react with oxygen, they can form two types of oxides. There is E2O3 and they can form E2O5 as well, okay? Now in E2O3, their oxidation state is +3, and in E2O5, their oxidation state is +5, which I'm sure that you would have gathered it. More is the oxidation state, what happens? More is the acidic strength. More is the oxidation state, more is the acidic strength. Remember it. What did I say here? I said that more oxidation state, more acidic strength. More is the acidic strength. Okay. So we see that everybody, have a look here. I will tell you. N2O3, this is acidic. Okay. N2O3 is acidic. P2O3 is also acidic. Right? But Bi2O3 is basic. Bi2, bismuth, Bi2O3 is basic. As2O3 and Sb2O3 are amphoteric. So as you go down the group, the acidic character decreases. Okay, acidic character decreases. All right, that's it about reaction with oxygen. You don't have to study further than this. Okay, but just remember that go through the list. Please go through the list. I'm marking this here. I'm marking this here so that you go through the list and you can write it down and practice a little bit. Here I don't have anything to teach you, but you also know how to calculate the oxidation state, right? That you have learned in the redox reaction chapter already. Okay, chalo guys. Now here let us talk about the JEE Mains 2019 question, which is the correct order of the oxidation state of nitrogen in NO, N2O, NO2 and N2O3. Okay. For NO, what is the oxidation state? Right here we have NO, oxidation state of nitrogen is +2 here. For N2O, what is the oxidation state, everybody? For N2O, it is +1. Yes. For NO2, what is the oxidation state? For NO2, it is +4. It is +4. And for N2O3, what is the oxidation state? +3, obviously, right? +3, obviously. So what do we have? We have N2O. Then we have NO, then we have N2O3, and then finally we have NO2. This is +4 oxidation state. So this is the correct answer. Now check it out. Which one is it? N2O, then NO, then N2O3, and then NO2. So option D is our correct answer. Option D is our correct answer. Why am I running like this, guys? That's because we have to finish the chapter quickly. I do not want to take so much time from you. Okay. Now we come to group 16 elements, that is the oxygen family. And did you know that just like how you call the group 17 elements as halogen family, group 16 elements are called as chalcogen family. Here what do you have? You have OSATPO. So you have oxygen, sulfur, selenium, tellurium, and polonium. Now oxygen and sulfur, as we all know, are non-metals. Selenium and tellurium, these are metalloids, and polonium is a metal which is radioactive. Polonium is not synthetic radioactive, by the way, guys. Polonium exists in nature. All right, polonium does exist in the nature, so polonium is definitely not a radioactive, synthetic radioactive element. It is not. All right. Yes, but I think this group also has a synthetic radioactive element. Does anybody remember it? What is it? Anybody remembers it? No? Yes? Anybody? Please let me know in the comment section, okay? If you can remember it, please let me know in the comment section. I would like to remember it again, because right now I have forgotten, and it's not a good thing. As a teacher, I should not be forgetting, but what to do? Your mind cannot take in so much of concepts and so many things that you want to learn, right? You cannot do that. Anyway, guys, let us talk about it more. Yes? Chalo. Moving on. Now, let us have a look at their general electronic configuration. What is the general electronic configuration? In this case, the general electronic configuration. Ah, I remembered it. Yes. The synthetic radioactive element is livermorium, LV, Louis Vuitton. Yeah. It's livermorium. Livermorium is the synthetic radioactive element. I have just remembered. Yes. And the general electronic configuration for this group is everybody NS2NP4, my dear students. So that means that they can show you +4 oxidation state. They can show +6 oxidation state as well. But apart from that, what else can they show? They can also show -2 oxidation state, isn't it? They can do that. All right. We will study about it. Now here is the electronic configuration. As you see, for oxygen it is 2s2 2p4, sulfur 3s2 3p4, selenium 4s2 4p4, tellurium is 5s2 5p4. For polonium, everybody, it is 5d10 6s2 6p4. So the general electronic configuration is clear, right? What happens to the atomic and ionic radii? The atomic and the ionic radii, they increase as and how it should. Okay, so how do they increase? They increase as O, then S, then it is selenium, then it is tellurium, and finally you have the polonium. So this is the atomic and the ionic radii. This is how they increase. Okay, this is how it increases. Chalo, guys. Moving on now, let us have a look at what do we have to study in this group. Now, once again, for this group as well, for the whole of group 16, there are certain questions which might be asked in your boards and which might be asked to you as an exception from this group. Okay, and these questions I've noted it down here, right here in the slide. So please go through them at your own time, revise them again and again, so that you are able to solve your board exams as well as your JEE mains, whatever they ask you. Okay, all right, please do that. Shall I move forward then? Shall I move forward, everybody? Will you all be able to do it? I hope so. Please do that. Okay, chalo, guys, moving on, everybody, moving on to this oxygen family. These are the solutions that I was telling you about here. Now here is a question. Like sulfur, oxygen does not show +4 and +6 oxidation state. What is the reason? Can you tell me? What is the reason? Any idea? What will happen, guys? What will happen? What will happen? Nobody? Nothing? Okay. That oxygen is a gas while sulfur is a solid. Really? No. That oxygen has high ionization enthalpy in comparison to sulfur. That oxygen has high electron affinity in comparison to sulfur. Oxygen has no d orbital in its valence shell. Absolutely. Oxygen is a second period element. D orbitals have not been introduced. But in case of sulfur, yes, there are vacant d orbitals. Okay, there are vacant d orbitals. Hence, you get to see that there are +6 oxidation state that is exhibited by sulfur. All right. Okay, guys. Okay. Moving on, here are sulfur allotropic forms. But before that, guys, we have to write down some notes which I'm writing here. Okay, I'm going to write it here for oxygen family. Okay. For oxygen family, everybody, like I told you, now oxygen can actually show you many other oxidation state as well. So first of all, let us talk about the oxidation state. Oxygen can show you -1/2 oxidation state when in case of superoxide. In case of superoxide, it can show you -1/2 oxidation state, right? It can show you -2, it can show you +2 when it forms a compound with fluorine, OF2. It can show you +1 oxidation state when it forms O2F2, all right, yes. And it can show you -1 oxidation state when it forms peroxide, and of course +6 oxidation state it can show, but not so much, right? But as you go down the group, especially for polonium, you will not be able to see the +6 oxidation state because of inert pair effect, which you already know. So oxygen can show many different various oxidation states, everybody. Okay, all right. Now, generally, the oxygen show -2 oxidation state. However, these all are the exceptional oxidation states. So please remember it. The tendency to show this -2 oxidation state that I'm talking about, this -2 oxidation state, it decreases. Polonium cannot show -2 oxidation state. Why? -2 means gaining 2 electrons. Polonium has a bigger size. Will it be able to gain electron? Electron gain enthalpy will obviously decrease as you go down the group because the size is increasing, isn't it? Exactly. Yes, absolutely. And due to the inert pair effect, the stability of the lower oxidation state, that is +4, once again everybody, repetition, you will see that it will increase, and the stability of higher oxidation state will decrease. You will see that, right? Yes, anomalous property, we already know. In case of H2O, there is H bonding, there is hydrogen bonding. However, in H2S, you will not see the hydrogen bonding. This is another exception of oxygen. Yes, this is an oxygen. This is only because of oxygen that you get to see this, okay? The other elements in the same group, they can expand their covalency, which is more than 4. They can do that, okay? All right. Now, when they react with hydrogen, oxygen, this family can form, and this family can form oxides which are of the form H2E. Okay. Yes. Now, what is their acidic character? Let's have a look at it. H2O has the least acidic character. Then it increases slightly, H2S. Then it increases for H2Se. Then it increases for H2 tellurium. Yes. All right, everybody. The size increases, overlap decreases, and the hydrogen is released easily as you go down the group. Hence, the acidic character is like this. The thermal stability, however, is just the opposite because H2O has a very small size, oxygen is of small size, the overlapping is strong, the bond is also strong. But as you go down the group, tellurium is of a bigger size, the overlapping is not so good, the bond becomes weak. Okay, the bond becomes weak. All right, everybody, clear hai? All of these things I'm telling you, everybody, please do note it down, and I have given you the notes previously as well. I've taught this chapter previously as well. Please go and have a look at them. All right, yes. Now we come to the melting and the boiling point. What will happen to the melting and the boiling point? Obviously, because of the hydrogen bonding, the maximum melting and the boiling point you will be able to see in case of H2O. Okay, all right, yeah, great. Now, does this group, do they react with oxygen? Yes, they do. They react with oxygen and they all form oxides. Now, what are the types of oxides they form? What are the types of oxides that they form? Chalo, that I will have to write it down here, okay? I'm writing it down here. Reactivity with oxygen, guys. Reactivity with oxygen. Reactivity with oxygen, and they form oxides of two types. They form EO2 and they form EO3. Now tell me, does oxygen form EO2? Yeah, O3, ozone. Ozone is what? O2 plus oxygen, isn't it? So O3. Then you also have SO2, that is sulfur dioxide. These are both gases. EO3 you do not get in case of oxygen, but you do get SO3. Then you get selenium O3. Yes, then you get tellurium trioxide O3. Yes, but in case of here, SeO2 and TeO2, did you know that these two are solids? Okay, these two are solids, whereas SO2 and O3, these are both gases. All right, everybody, clear? Chalo, now moving on. Now, let us have a quick look at the sulfur's allotropic forms, everyone. If you all are ready, let us take a quick look at sulfur's allotropic form. Yep. Okay. So in case of sulfur, we see that sulfur has two allotropic forms, that is alpha sulfur and you have beta sulfur. Yes, now alpha sulfur is stable at room temperature, S8, And the sulfur is formed, beta sulfur is prepared from the rhombic sulfur, that is the alpha sulfur, and in a dish and cooling till crust is formed. Okay, two holes are made in the crust and the remaining liquid is poured out. On removing the crust, you get the colorless needle shaped crystals of beta sulfur. So everybody, once again, the beta sulfur has needle shape, all right, and the rhombic sulfur crystals are formed evaporating the solution of roll sulfur in CS2. This rhombic sulfur is yellow in color, yes, and it is insoluble in water, but it dissolves to some extent in benzene, alcohol, and ether. It is readily soluble in CS2. Okay, all right, and there is a temperature which is called as 369 Kelvin. This 369 Kelvin is where the rhombic sulfur and the monoclinic sulfur, that is alpha and beta sulfur, both of them are found in equilibrium. All right, they're found in equilibrium. Now, once again, everybody, I am just showing you the pictures of oxo acid. Although I know that it will not come, it's not included in your syllabus, but I'm still giving you the list only if and only if by chance they ask you about the oxidation state of oxo acid, then here is where you have it. Calculate it and write it down, please. Okay, I'm just giving it to you for your benefit, and I know for a fact that nobody else, none of the other teachers are going to show you this, because I don't know, it's a waste of time, I believe, but please do go through it once. I don't want you to feel chaotic when, if at all, one question comes from, you know, P block and redox. If it is merged like this, you should be able to attend the question. So please just go through it, okay? Alright, then we come across group 17 elements. Group 17 elements is basically your fluorine, chlorine, bromine, iodine and astatine. Yes, and you know that fluorine and chlorine, they are gases. Bromine is a liquid and iodine and astatine, these are solid. Yes, the general electronic configuration for this group is NS2NP5. Everybody, astatine is radioactive, but it's not man-made, it is not synthetic. Okay, these group 17 elements, they are collectively known as halogens, which we all know it. Halo means they can produce salt. Okay, yes, they can produce salt, everybody. They are called as the birth givers or the salt producer. And you know that fluorine exists or occurs as fluorspar. It can occur as cryolite, it can occur as fluorapatite, right? And chlorine, it is obtained from dried sea contents. What is it? NaCl, sodium chloride. Where do you get it? Samandar ka pani. Yes, you have sea water, just dry it up, you will get NaCl, isn't it? And sodium chloride, that means chlorine is present in it, right? Okay guys, get. Once again, in this case also, the electronic configuration I've already told you. Now, if you look at the properties here, you will find that covalent radii here for fluorine is very small. It is just 64 picometer, and that means that fluorine yet again will be showing you anomalous behavior. Okay, and we know that the atomic and ionic radii is very simple. Fluorine has the smallest, then chlorine, then bromine, then iodine, and then astatine. Yes, ionization enthalpy, electron gain enthalpy, I think we have spoken about it already in periodic properties just some time back. Please go ahead and watch it from the beginning. Okay, please go ahead and watch it from the beginning. Now, here are certain physical properties that you should know is that fluorine and chlorine, okay, fluorine especially is a gas. Fluorine is yellow in color, everybody. Fluorine is yellow in color. Chlorine is greenish yellow in color. What is chlorine? Chlorine is greenish yellow in color, everybody. Bromine is a liquid and it is red in color. Iodine is solid and it is violet in color. Okay, yellow, greenish yellow, red and violet. Okay, yellow, greenish yellow, red and violet, related colors. I think you can remember it. Okay, alright guys, so physical property, we all know that fluorine is supposedly the most electronegative element. The melting point and the boiling point increases as you go down the group with atomic number, because here what happens is the strength of the van der Waals force increases with the increase in its mass. Yes, with the increase in mass, we see that the strength of the van der Waals forces here increases. The density also increases as you go down the group. And what happens is all of these elements, I just told you that they show you different color. Do you know why? Because here what happens is they can absorb radiations in visible region, and that results in the excitation of the outer electrons. The last electrons, yes, they can get excited, they go to higher energy level, and by absorbing different quanta of radiation, they can display different colors. Okay, all right. Apart from that, now bromine and iodine, they are only sparingly soluble in water, but they are soluble in various organic solvents such as chloroform, CCl4, CS2, and hydrocarbons to give colored solution. Okay, they give colored solution when they get dissolved in these. Okay, all right, everybody, cool hai? ठीक है, understanding or not understanding? Is there any issue? I hope there is none. I hope there is none. Is there any issue? No? Yeah? No, right? Okay, great. Now down the group from chlorine to iodine, the bond dissociation energy, it decreases in the order ClCl, Br, Br, I, because why? The bond length increases. As you know that as you go down the group, what happens? The size increases. If the size increases, that means that the radius will also increase. The bond length will increase. And if there is a longer bond length, it is easier to break, isn't it? Hence, the bond dissociation energy decreases. The bond dissociation energy of fluorine-fluorine bond is a little less than chlorine-chlorine. Why? Because the electrons are so close. Fluorine has such a small atom. Electrons are so close that they will try to repel each other, but that does not happen in case of chlorine. That is why the bond dissociation energy of fluorine will be slightly lesser than chlorine. Okay. Alright guys, let us try to solve this question. The question is, which one of the following order is correct for the bond dissociation enthalpy of halogen molecule? I think I've just told you. It will be chlorine, then no, it will be, fluorine will have the least. So it will be, what do you think guys? What is the answer? Chlorine will have a great bond dissociation enthalpy, then it will be bromine, then it will be fluorine, and then iodine. Right? Yes. So I think that option B is the correct answer. Yes, absolutely. Absolutely. Correct answer is option B. Chlorine will have higher bond dissociation enthalpy than fluorine. And we know that from chlorine to bromine, it decreases. Yes. And then from bromine to fluorine, it decreases. And iodine will have the least because iodine has the biggest size in the group. Okay. Great. Next question. Among the following, which is the strongest oxidizing agent? What do we know here? What is the answer here, guys? Come on, let us think about this. This I really, really want you all to answer. Huh? I really think that you can all answer. Come on, guys. Come on. What do you think is the correct answer here? Which one will be the correct answer? Which of the following is the strongest oxidizing agent? Don't you think it is fluorine? I think it is fluorine. Of course it will be fluorine, right? Fluorine will be the strongest oxidizing agent. Absolutely. Yes, that is the correct answer. What are you thinking? It has to be fluorine, guys. It has to be fluorine. Chalo. Moving on, everybody. Chemical properties of the group. Let us talk a little bit about the chemical properties of the group. What do we have here? Acha. Now, in this case, in case of chemical properties, we do know that they can react with oxidizing nature of halogens. They can oxidize, right? I have just given you the question, but now I'm going to explain this to you. Fluorine has a very high oxidizing nature because of low bond energy of fluorine. Yes, there is a low bond dissociation energy we just saw, and it has also high hydration enthalpy of fluorine. Whenever the atom is very small, water molecules can come and attach to it very easily. That is why we say that high hydration of fluorine. Now, F2 can oxidize the other elements of the group as well. Yes. How? Like, check it out, check it out. See, F2 plus Cl minus, if you take, what will happen is it will form Cl2 and it will form F minus. Right? Now, if you have here F2 plus here, if I write here Br minus, see what it will do? It will do Br2 plus F minus. It can do this also. Now, if I have Br2 plus I minus, did you know that this can also happen? It will have I2 plus Br minus. This can also happen. Okay. These group elements, they do react with water, yes, and they form HF plus O2. For example, if fluorine reacts with water, F2 plus H2O will give you HF plus O2. If Cl2 plus H2O reacts, if Cl2 plus H2O reacts, then what will happen is you will get HCl minus, not HCl minus, you will have HCl where the oxidation state of Cl is -1, plus you will also get HOCl where the chlorine has +1 oxidation state. Okay. Similarly for bromine, then in case of I2 plus H2O, it does not give you any reaction. Okay, it does not give you any reaction. So do we see that chlorine, when it reacts with water, it forms hypohalous and hydrohalic acid, both. It disproportionates. Okay, this is a disproportionation reaction. Cool. All right, everybody. Yes, anomalous properties of fluorine. I think that you already know about it. I don't have to teach you. Reactivity of halogen towards hydrogen. This is important. Yes. So the this whole family, the halogen family, when it reacts with hydrogen, it forms HX, right? It forms hydrogen halide, like HF, like HCl, HBr, HI, and when they react with water, you get hydrochloric acid, hydroboric acid, all of that sort of, right? Yes. Now what happens here is this HCl, HBr and HI. Yes. The boiling point here is slightly twisted. Do you notice that for HF it is much higher? Why? Because of the hydrogen bonding. But for HCl, HBr and HI it's slightly twisted. It increases, increases, increases. Why? Why does the boiling point increases? Because of van der Waals forces. The van der Waals forces increases, helps, sorry, the boiling point also increases. Okay. All right. Now, stability. As you go down the group, the bond length increases and the bond strength decreases, which is why HF has higher stability and HI has the least stability. Okay. Acidic strength. HF will have the least acidic strength and HI will be the highest. Why? Because bond strength is now much lesser. Hydrogen will be released very easily. Cool. All right, guys. Now we are going to talk about the reactivity towards metals. Yes, let us talk about the reactivity towards metals. These halogens, they react with metals, right? They react with metals. Why so and how? So the halogens, they react with metal and they also react with non-metals, by the way. They do react with metals as well as non-metals and they form what? Like sodium plus Cl2 will form sodium chloride. Aluminium plus Cl2, you will see AlCl3. You will also see that sulfur and chlorine, they react and they form 4s2Cl2. So yes, they can form halides with both metals and non-metals. Okay. All right. Yes. Now moving on, what do you have? What do you see? You see that Mi has a very, very, very low ionic character, because we know, right, Fayon's rule. Everybody knows Fayon's rule. Yes, covalent character, how do you get it? Small cation, large anion, right? Now in case of MF, everybody, that is a monovalent metal with fluorine, you will see that it is ionic. Why? Arey, covalent character is small cation, large anion. The opposite of it will be what? Large cation, small anion. Here, don't you see that fluorine? Fluorine has a very small size. So, small anion, large cation will give you an ionic product, isn't it? That's exactly what it is showing. Yes. So, I have just explained. Here, you have the Fayon's rule that you can read it later. I have already explained to you in one sentence. Okay. Yes. All of these are, I have just explained, if a metal exhibits more than one oxidation state, the halides in higher oxidation state will be more covalent than the one in the lower oxidation state. Just explained once again, just explained, yes. Now, do the halogens, they react with oxygen? Oh yeah, absolutely. Why not? Yes, they do react with oxygen and they form oxides. Yes, they form oxides. And I have just told you, right? What are the oxides? You have OF2, you have O2F2, you have Cl2O, you have ClO2, you have ClO3, you have Cl2O7. All of these are there. Why? These F2O2, O2F2 and OF2, these are good fluorinating agents. What do? They are good fluorinating agents. Okay. All right. In case of chlorine also, it's here. See, Cl2O, ClO2, Cl2O6 and Cl2O7. In Cl2O7, what happens? Chlorine shows +7 oxidation state. In Cl2O6, you can calculate that. Please calculate. ClO2, it will be +4. And in case of, sorry, written in the wrong part. ClO2, it will be +4 oxidation state, and Cl2O, it is +1 oxidation state. This, figure it out, calculate it on your own. It will be a good practice if it comes, okay? Alrighty guys, now we know that ClO2 is used as a bleaching agent for paper pulp and textiles and in water treatment. Yes, these are highly reactive oxidizing agent, okay, and they tend to explode. They tend to explode. Alright everybody, yes. Reactivity towards halogen. Okay, continuing. Bromine oxides like Br2O, BrO2 and BrO3, what are they? They are the least stable halogen oxides. They exist only at low temperature and they are very powerful oxidizing agent. Okay, just read through them. That's it. You don't have to do much. Yes. Now here, oxo acids of halogen. Once again, here is a list, everybody. All the oxidation state of halogen is noted down here. Please go through it. I'm not going to teach you here because it's not there in your syllabus, but I need you to go through it. By chance, if there is any question, you should be able to attend it. Now, the bleaching action of chlorine is due to what? The bleaching action of chlorine is due to why? Why is there? Reduction, hydrogenation, chlorination or oxidation? Guys, it has to be oxidation, isn't it? Yes, it has to be oxidation. The bleaching action of chlorine is due to oxidation. Yes. Chalo. And finally, we have come to the last bit of this lesson, that is, my dear students, our group 18 elements. Okay, the group 18 elements we have reached, everybody. Let us have a look at it. Chalo. Interhalogen compounds, by the way, are not present in your syllabus, so you don't have to study. These group 18 elements, they were also called as the zero group elements, and they form very few compounds, and only usually xenon forms compound, right? So you have Hina, Nina, Arite, Carina, Xerox, Radon, that is helium, neon, argon, krypton, xenon and radon. Radon is the rarest element of the group and this is radioactive. However, just below radon, you also have Og, that is oganescent, and that is a synthetic radioactive element, okay? And we all know what is the general electronic configuration. The general electronic configuration is, everybody, Ns2Np6, right? Ns2Np6, okay? Their ionization enthalpies are much higher, their atomic radiuses are also very, very big, and their electron gain enthalpy is also much, much, much lower here, okay? Yes, everybody, why the ionization enthalpy decreases down the group even more as the size increases? Because of the stable electronic configuration, these gases, they exhibit very high ionization enthalpy. They do not want to mess up with the stability. Atomic radius increases down the group. They have no tendency to accept the electron and therefore they have large positive values of electron gain enthalpy. All these noble gases, what are they? They are not at all reactive, so that means that they are monoatomic and they are colorless, okay? They are colorless. All the noble gases, they occur in the atmosphere except radon, okay? Except radon. Helium and neon sometimes are found in the minerals of radioactive origin as well, okay? And radon is obtained as a decay product of radium, okay? All right, yes, okay. Now everybody, moving on, what is their atomic radii here? Their atomic radii, everybody, is van der Waals radius, and this is non-polar and neutral. Van der Waals radii, as we know, is the biggest. It is bigger than the metallic radius and it is bigger than the covalent radii. Top to bottom, the size increases, so that is done any which ways. Yes, that is done. You don't have to study about that at all. We already know about what is what and what is not, right? Yes, guys. Now, yes, what else? They have very low melting and boiling point because of the weak dispersion forces. Because of the weak dispersion forces, right? You all know that, right? Boiling point increases down the group with increase in strength of the dispersion forces. Helium has the lowest boiling point. Completely filled electronic. I feel like it is repetitive. I mean, we know that already. Chalo, one question, let's solve. Noble gases, they do not react with other elements because they are completely paired up and stable electron shells. I mean, that is going to be the answer. Oh, we are already done. With this note, we have come to the end of the session, guys. So the noble gases was the very small part of the, very small part of the whole session. You don't have to worry about it at all. I don't think from noble gases you will be asked any question whatsoever. And now that xenon compounds are not there, the chances of asking a question from noble gases has reduced almost to the bottom. what they might ask you is, there are chances of you getting a question related to the thermal stability, the acidic strength, you getting a question related to the isoelectronic species, you getting a question about where will you put the element if it is not discovered. There is a very low chance, but you might be asked about the synthetic elements like 101, 112, how to name these elements and how do you know it, how do you do it, un Nilium, right? And you know how to name all of that. Those rules are very easy. I think you can just go through it once and you will get to know about it. So that's it. These are the only type of questions that they may ask you. And from P block, what else can they ask you? Yes, they may ask you about the hydride's strength. They may ask you about the oxidation state, something related to inert pair effect. These are the questions, these are the topics. Please go through them once. And finally, everybody in Vedantu, we all know that we have just launched JEE test series, which is absolutely free of cost. It is a computer based exam. JEE exam pattern it will follow, and it will also follow the JEE new syllabus. So it is free of cost. Just go and attend the test. Nothing you will have to lose. And every single day we are sending you DPP. It is just below this video in the description box. You will find the DPP. It's a daily practice paper. There will be 10 to 15 questions. Please go and attend it so that you get to know and you get to check your own strength and weaknesses. Please go ahead and do that. And with this note, everybody, thank you so much. Tata, bye bye. Very sorry that I could not take the live session, but I hope that I have recorded it and you were able to follow it very well. So thank you so much, guys. I'll be sending you the PDF in the Telegram channel, so do join the Telegram channel as well. Bye, see ya.